So if you see this diagram, at this stage you should able to connect directly. So this is a basic definition of power electronics. Okay, so you take any power electronic circuit, basically it has a source and load, right? And power electronic circuits, we can simply say that these are power processing circuits. What is the basic function of this power processing circuit? Whether it is a rectifier, chopper, inverter, whatever the circuit you take, the basic idea here is it will process the power. That means it will convert and control the source power in order to match with the load power, and depends on the application. And for this process, what are devices in this block? Of course, semiconductor devices at power level. So throughout this course, you take any power electronic circuit, it is comprising of power semiconductor devices. Basically they will operate at the power levels in order to fulfill the given objective. Okay, so after this, what we discussed, the applications of power electronics. Now if you go through all of these applications, what is the takeaway? That is, power electronic circuits will have applications from very low power levels to very high power levels, right? And all of these applications spread across the starting from generation to till end consumer level by using power semiconductor devices. Okay, so in this lecture we discussed what are all the applications in a systematic manner. Quickly I can say the basic applications are drives. Next, power systems, basically these are fax applications, and transportation, basically electric vehicles and all. After that, domestic and renewable energy systems, right? So in all these applications we can consolidate in a single diagram. So this diagram will tell you that quickly. Power electronics have applications from low power to high power, and these applications spread across generation to till end consumer. Okay, so in this video what you can understand is the sequence of the previous lectures. So the 50 videos of class, now we will consolidate in 4 videos of class. Therefore I will not going to write any equations. So what all the notes, detailed notes I gave, so I will use that. So quickly, if you have your own running notes when you prepared during the course videos, you just go through, just turn the pages, right? So advantages and disadvantages of power electronics. So if you see advantages and disadvantages, the main motivation here is power electronic circuits will have very less losses. That is due to power semiconductor devices operates as a switches. Due to the switching operation, it will give with one drawback. What is that drawback? Harmonics, right? So with that discussion, we studied about power electronics definition and all. Okay, so advantages and disadvantages, the reason is the same. Power semiconductor devices are operating as a switches. Due to the switching action, it will give you less losses. At the same time, it will give you harmonics. Now this harmonic discussion is very important, not only from power electronics subject, it is important for signals and systems also. Okay, so during your preparation, my sincere advice is you spend good amount of time for Fourier series analysis. Okay, so this is the basic definition of Fourier series analysis. In this definition, there are few key terms. First term is A naught by 2. What is that A naught by 2? You can also say that it is a average value or DC component. Okay, and another thing is AN. AN definition is given here. Okay, so you should be in a position to calculate AN value either from integration or by looking into symmetric property of the waveform. Okay, in the similar manner, another important term in the Fourier series discussion is Bn calculation. Okay, so Bn definition is here. So anyhow, in our class we have not discussed in detail how to identify the symmetry property of a given waveform. The reason is that particular piece of Fourier series is will be explained in a signals and systems subject. Okay, so at this stage my sincere advice is it will be useful for both power electronics waveforms as well as signals and systems subject. So what you need to identify at this stage. So what are the different types of symmetries here? Odd symmetry. One type of symmetry is a odd symmetry. Another is even symmetry and half wave symmetry. Okay, even symmetry and half wave symmetry. So these are important symmetry, how to identify and all. I think you might study it in a signals and systems subject. Okay, now from the Fourier series point of view, what are some standard waveforms are more important from power electronics subject. Okay, those are square waveform, delayed square waveform, quasi square waveform and half wave rectified, full wave rectified waveforms. Okay, so we had discussed about those waveforms in detail in the regular class. Okay, so this is a quick conclusion. Anyhow, this notes is available with you. You can quickly go through those documents. Okay, so what is the conclusion from these two waveforms? Important thing is these two waveforms contains odd harmonics. These two waveforms contains odd harmonics. What are these two waveforms? Square waveform and quasi square waveform. Okay, and DC component is 0 for these two waveforms. DC component is a 0. So for these two waveforms, DC component is a 0, right? So another important thing is fundamental component is important. Okay, what is fundamental component here? This magnitude. What is the fundamental magnitude? 4x by pi, right? 4x by pi. That x value depends on the application. Okay, so you will get these waveforms in the later circuits. What are those circuits? Inverter circuits, you will get these waveforms. Rectifier circuits, you will get these waveforms. In the rectifier circuits, you will get these waveforms in the source current side. Okay, now coming to quasi square waveform, we will get quasi square waveforms in the single phase semi converter circuit, source current waveform, and 3-phase full converter source current also you will get quasi square waveform. Coming to inverters chapter, 3-phase inverters, phase voltages and pole voltages in different operations. Okay, 180 and 120 degree conduction modes, we will get these waveforms. Here also fundamental component magnitude is very important. Suppose if you substitute n is equal to 1 in this particular term, it will give you the magnitude or amplitude of fundamental component. Okay, next another important waveform is half wave rectified waveform. So the differentiation between these two waveforms is first 3 waveforms, square, delayed square, quasi square, will have odd harmonics, but half wave rectified waveform are not having odd harmonics. It will have only even harmonics. Okay, now suppose if you see half wave and full wave rectified output voltage waveforms, what is the important comparison between these two? Okay, so here in this full wave rectified waveform, if you see fundamental component is absent. Fundamental component is absent. That is one of the important comparison in these two waveforms. Okay. So I hope you might solve these skill assessment problems. 6-step square waveform, and this waveform you will get in the choppers chapter. Anyhow, that is given for your exercise, right? So up to this, what is important aspect for exam point of view? Fourier series analysis for different types of waveforms. Again, I am stretching. Whenever you are seeing a particular waveform, you should be in a position to quickly identify what is the type of symmetry the given waveform contains, right? That is half wave, odd symmetry and even symmetry. Some waveforms will have the combinations of half wave plus odd symmetry. It is called odd quarter wave symmetry. Some waveforms will have half wave plus even symmetry. It is called even quarter wave symmetry. Okay. Now, the next thing what we discussed in our regular class is switches. We discussed a good amount of time about switches, right? So the switch discussion, how did we separated? That is switch properties. Okay, ideal property and real switch properties. What are these properties? So there are basically 5 main properties. What is that? Let us go one by one. On state, ideally switch will not have any voltage drop, right? In the on state, switch will not have any voltage drop, and ideally it can carry any amount of current. Because of this zero voltage drop, ideal switch conduction loss will be 0. Okay, ideal loss, conduction loss will be 0, right? But in practice, this on state voltage drop is not equal to 0, okay, in real conditions. So because of that, it will contribute some amount of conduction loss. That is the difference from ideal to real conditions. Coming to off state, the basic property is the current flowing through the switch is 0, and a switch can carry any amount of switch can block any amount of voltage. Because of 0 current, you can say that blocking loss is equal to 0. But coming to reality, this value is not equal to 0. This is in real condition. Okay, due to the non-zero current flowing through the switch in the off state condition, there is some amount of blocking losses. Okay, now another property is it will talk about transition behavior. Okay, it will talk about a transition behavior. Ideal switch can change its state instantaneously. So you can say that switching times are 0 and the switching frequency will be infinity. And ideally there is no need of external circuit. Of course, these things are not possible practically. There are deviations that we discussed in the real switch properties. What about thermal constraints? As the switch has no power loss, the heat dissipated from the switch in its entire operation is 0. Therefore, ideal switch can operate anywhere in this entire IV plane. Okay, but due to non-idealities of the switch, coming into the real scenario, due to non-idealities, what is the consequences? Switch will have some conduction loss, switch will have some blocking loss, and switch will have some transition times. Correspondingly, it will have some switching power loss. Okay, due to the switching power loss, conduction loss and the blocking loss, some amount of heat will be dissipated. Therefore, the switch should be operated within some boundaries. That boundary is called safe operating area. Okay. Now, after this, we discussed about what type of components are preferable for switching transitions, right? Now, in this diagram A and B, we learned that when the switch is turned on and turned off with a resistive load, there is no sudden transitions between voltage and currents, and there is no harm to switching action. Now coming to C and D. So this will tell you that turn on transition with capacitor results into overcurrent. Turn off transition with inductor results into over voltage. We should avoid that. Okay. But what switching actions or what components are preferable here? In order to turn on the switch, inductor is preferable. In order to turn off the switch, capacitor is preferable. Okay. Now by using these concepts, we developed what components are preferable for switching action. So previous points, if you put it in one systematic way, we had a concept called snubber. Okay, this is a basic snubber circuit. Now in this particular case, this inductor is good for the switch during turn on transition, and this capacitor is good for the switch during turn off transition. Okay, so what is different types of snubbers and what are its basic purpose? So you can simply remember that whenever you placed inductive snubber, it will protect the switch against sudden changes of currents. That is also called di by dt protection. If you use capacitive snubber, it will provide the protection against sudden changes in voltages. Okay, so that will be called dV by dt protection, right? That is about a switch transition properties. So during this switch transition, as voltage and currents are non-zero values, it will contribute some power losses. We will see that. Now these definitions are very important. Average and RMS values are very important, not only in power electronics subject. Again, I am stretching for different types of waveforms, whatever the formulas and procedures I explained in the videos classes, you try to practice average and RMS values. So in this power electronics subject, Fourier series calculations very important, and average and RMS values are very important. So how to calculate average value? First you have to calculate area of the given function for one cycle. That area should be divided with cycle time. Then it will give you average value. So square of the mean value first. Okay, so mean of square of the function. If you take a root for that, then you will get RMS value, right? Now, so these are some of the conclusions for standard waveforms. Okay, so very important. Triangular waveform, magnitude square by 3 multiplied with function duration upon total cycle time, total under root. Next one, rectangular waveform and quasi square waveform. So if you practice these particular waveforms specifically, I am sure you can able to find RMS for any functions. Okay, RMS values for any function. And another thing is, when the switch is modeled with different components, resistor, voltage drop, and combination of these two. Okay, combination of these two. How to find power loss? This is another general place of mistake. Most of the students will commit mistake. So what we discussed in our classes, if the switch is modeled with a resistor, you have to use RMS value of current. When the switch is modeled with voltage drop, you have to use average current. Combination of that requires both average as well as RMS currents. Okay, so in this way you can calculate the switch power losses. Okay, and here I gave some problems. I hope you might solve it. So see, through mails most of the students asked how to solve this problem. Okay, so here what is the question? Voltage and current transitions are given. You need to find peak instantaneous power loss. I hope you might already done it. If not, at least practice now. From the current waveform, first write down current equation. in terms of t. Okay, express current equation as a function of time. Similarly, voltage equation in terms of time, okay, as a function of time. So what is the question here? Peak instantaneous power loss. What is power? V multiplied with I. Peak value, how can you calculate? So differentiate power with respect to time and equate to 0. So you will get some time value. At that time, if you find V into I, then you will get peak instantaneous power loss. Okay, it is not a difficult problem, but a good concept. Now, in this case, you will get what are the procedures or how to define energy losses during on transition as well as off transition. From that, how to calculate switching power loss. Okay, so from this equation, what is the takeaway? Whenever switching frequency is increased, switching power loss will increase. Therefore, in a semiconductor device, this is very important statement. Switching power loss in a semiconductor device varies linearly with the switching frequency and switching times. So, in order to have less amount of switching power loss, it is preferable to have devices with less values of switching times. Generally, that property is exhibited by power MOSFET. Okay. Now, so of course, various losses how to find, we can get it through this diagram. Now, in the sequence, the next topic is types of switches. Basically, types of switches are divided into two categories. One is based on control property, another is based on operating points. We'll see that next. So, what are the three categories? Uncontrolled switch, semi-controlled switch, and fully controlled switches. So you can go through the definitions quickly. Uncontrolled, there is no control property. Semi-controlled, only one state can be controlled. Fully controlled, both the states can be controlled. So for uncontrolled switch, example is a diode. Semi-controlled switch, example is a CR. Fully controlled switch, GTO and transistor family devices. Okay. Next category is based on operating points. Okay. So based on operating points, what are different types of switches? Unipolar, bipolar, unidirectional and bidirectional switches. Okay, so these are basic classification. So each switch comes under what category, that you need to make a small table, right? Now, if you go back and see what is the important points that we need to remember in the power transistor as a switch. So coming to power transistor and signal transistor, if you have a comparison, this quasi-saturation is one additional feature in power transistor. Second breakdown is another important feature of power transistor. Okay, due to that second breakdown property, power transistor will exhibit negative temperature coefficient of resistance. Because of that, it is not suitable for parallel connection. Okay, now what we need to understand or take away from these diagrams, in which region power transistor will operate as a switch, that is hot saturation region. In which region it will operate as a turn off switch, that is in the cutoff region. Previous one is a for turn on process. Now one important thing is power transistor, it will have thicker base region. Because of that, beta value is very low. Okay, so when beta value is very low, what is the consequence? It requires more amount of power for base drive condition. Okay. In order to overcome that, what is the common practice? That is, by this time you should able to identify what is this circuit diagram. This is a Darlington pair. So these type of Darlington pairs will be used to increase the overall gain. The expression for this overall gain is beta total is equal to beta 1 plus beta 2 plus beta 1 into beta 2. These are important points that we need to memorize. Okay. Now coming to power MOSFET, I have given 4 categories of power MOSFET. One is a N channel and P channel, enhancement and depletion. Like that there are 4 power MOSFETs, and these transfer characteristics diagrams important not only in power electronics, these are important in the analog electronics also. Now out of these 4 MOSFETs, we concluded that N channel enhancement MOSFET is best suitable for power electronic switching applications. Okay. Next one is IGBT. So power BJT has less amount of conduction losses. MOSFET has less amount of switching time. MOSFET drawback is it will have more conduction losses. Okay. Therefore, the combined properties are exhibited by IGBT. Okay. So this is another hybrid device we can say. Now remember, in the first chapter, most of the people will try to spend much energy on the device physics. Coming to the power electronics subject, you treat the given power semiconductor device simply as a switch. Device physics is not the more emphasis here. Okay. So you can just have overview of each device, and a more important point in this power electronics subject, that is, we need to understand what are the different types of switching waveforms, how to find average and RMS values of those waveforms, how to find different types of losses from the given conditions, how to find different types of harmonics are there in the given waveform by identifying a symmetric property of these waveforms. In that direction you should revise. Okay, your preparation should be in that direction, right? Now device by device, based on the safe operating area, you can conclude. Okay, diode comes under uncontrolled switch, unipolar and unidirectional switch. BJT and MOSFET, these are comes under unipolar and unidirectional switch, but these are fully controlled switches. SCR and GTO, SCR is a semi controlled switch, GTO is a fully controlled switch. Both comes under Thyristor family devices. Okay. Another important Thyristor family device, that is a triac, and when you consider MOSFET and IGBT with body diode, it will simply behave like a unipolar and bidirectional switch. Now in this particular switch topic, important thing, and there are 3-4 times GATE exam we got the questions. Okay, different switches are connected in some fashion. You need to identify what are the steady state operating points. Okay, so when the switch is on, from where to where current is flowing, is it a one direction or both the directions, that you need to identify. When the switch is turned off, whether the switch is able to block one polarity of voltage or both polarities of voltage, accordingly you need to take the decision. Okay, switch concept is very important, especially for this GATE exam. So different types of switches or devices are connected in order to realize one particular property. Such a switch is called composite switch, right? So I gave one skill assessment problem here. Draw a 4-quadrant switch realization using BJTs. I hope you might done it. If not, you just try this again. I will give you a hint. So 4-quadrant switch is nothing but two SCRs placed anti-parallel or back-to-back connection, just like a triac. For one SCR, we discussed two transistor model. So in one SCR place, draw two transistor model. That combination draw in a reverse fashion for second anti-parallel thyristor. Then you will get the answer for that. 1.7, it is not a difficult question, it is an easy question only. Now, another important properties for power electronic circuit understanding. See, any power electronic circuit you can visualize in a high level. It was designed by using three major components: inductor, capacitor and any power semiconductor device, that depends on the application. Therefore, in order to analyze these power electronic circuits, we should be clear in the inductor and the capacitor concept. Okay, inductor operates on volt second balance concept, which is also called flux balance concept. Okay, that means in the steady state this definition is very important. So in order to inductor to operate in steady state, the final value should be same as initial value of one particular cycle. In the similar way, capacitor will operate in amp second balance or charge balance equation. Okay, anyhow, in the next page I gave this table. See, during the revision these type of table making is very important. It will give you quick revision for different formulas. So inductor volt second balance, capacitor amp second balance. You will use these concepts thoroughly in the Choppers chapter. Okay, the Choppers chapter. So in this particular two diagrams, what is this one? It is a simple 0. It is a simple pole. These Bode plots will explain you about simple pole, simple 0 and a simple pole for inductor as well as capacitor. Okay, and I hope you might try this problem. Now coming to skill assessment problem 1.9, it's a very interesting question. If you try it, it is well and good. Otherwise, at least try it now. Given waveform is voltage across capacitor here. So what you need to find? Power loss in the capacitor. Okay, power loss in the capacitor. Strictly speaking, in an ideal capacitor there is no power loss, but due to this, generally this is called ESR, equivalent series resistance. So what you need to find out? Find current flowing through this capacitor. Okay, that means if you draw current flowing through capacitor by taking this as a voltage waveform. Okay, I will draw rough sketch here. You will get capacitor current waveform will be something like this. Okay, capacitor current waveform will be something like this. This is a blue color waveform is a capacitor current. So you have to identify the magnitudes, that is the question. From that waveform calculate IRMS, then square it, and ESR value is given, that I square R multiplied with R will give you power loss. That value is 3.64 watt. I think some of you have already done it. If not, you try it out. Even this problem, this particular question, not only important from power electronics point of view, from networks point of view also, it is very important. Now from this lecture onwards, overview of devices and device physics. Okay, as I told already, device physics is not that much weightage in this GATE exam for power electronics subject. Okay, so what you need to understand here in the high level, what are the different devices in power electronics subject? There are, it can be classified into two major categories. One is majority carrier device and minority carrier device. in what way power electronic devices are differentiated from analog electronic devices. Okay, that is, the major difference is the presence of lightly doped material. Okay, so what is the reason for lightly doped material? In order to achieve high breakdown voltage property, in order to achieve high voltage breakdown property. But because of inserting that lightly doped material here, what is the problem? Conduction loss is high, right? So that can be overcome in the minority carrier devices. Okay, so in this case also lightly doped material will be used, but conduction losses are less. That is due to a specific process is called conductivity modulation. So in the high level, what is required for us? You have total devices in our subject. What are that? Diode, MOSFET, IGBT, SCR, GTO and triac. These are the 6 devices that we will come across in power electronics subject. Okay, in these devices, as per the constructional diagram, which devices will have conductivity modulation concept, which devices are not having this property. Okay, so the devices with conductivity modulation are also known as minority carrier devices. In those devices, conduction losses are less, but switching times are more. Okay, but in the devices where this process is not there, in those devices on state losses are more, but switching times are very less. That is MOSFET. Okay, in that way you can memorize it. Okay, so the next class was on power diode. What is the important aspects in this power diode? Suppose if you see this power diode, the important aspect is the presence of this n minus layer in power diode. That is the only difference. Due to the presence of that n minus layer, during the turn off characteristics, it will have a different properties. We will see that. Okay, so this is about IV characteristics. Now slope of this particular line will be the reciprocal of on resistance of the device. Okay, now here there are two important aspects of this construction. One is non-punch through, another is a punch through diode. Now just read this statement. If the length of this particular drift region, what is that drift region? Lightly doped n minus region. Okay, if this width of drift region is longer, this is important word, okay, is longer than depletion layer width at the breakdown. Okay, such construction is called non-punch through diode, right? But if WD, right, what is that? Width of depletion layer is less than the depletion layer, width of the drift region is less than depletion layer, then it is called punch through diode. There are two types of constructions in the power diode. You will get these terminology in the later, that is the IGBT also. Okay, so that is the presence of buffer layer and absence of buffer layer. So this is about power diode. One important aspect in case of power diode is a conductivity modulation. Anyhow, we had a detailed explanation for that one in our lectures. So what is important thing we need to remember, and a few equations, those are switching characteristics of power diode. In the switching characteristics, there are two terms are very important. What are that? One is QRR, reverse recovery charge, and TRR, okay, reverse recovery time. So the switching properties of a power diode basically depends on this TRR. Now during this turn off process, if VRP, reverse peak voltage, is very much a higher value, In order to control that, we need to have a snubber circuit. Okay, so we had some derivations for these characteristics. So you need to memorize these equations IRR and QRR, and we have also done some problems on this. So from power diode, these equations are important and associated problems. Even one more point, till now in the GATE exam on power diode there are no questions on these variables, but in engineering services exam there are some questions. So you can expect, this is one of the non-touched area in case of GATE exam. You can expect this question maybe, right? So there is a classification of power diodes: general purpose diode, fast recovery diode, and silicon carbide diodes. And during the selection of power diode, what are the parameters that we need to consider? Okay, there are 7 properties. Anyhow, these are not so much weightage for GATE exam. Now coming to SCR, next very much important device, especially in our subject, that is a SCR. So you can visualize this constructional diagram, and from this, what is these layer properties? So here also the important thing is n minus layer. So the voltage, forward voltage as well as reverse voltage blocking properties will be decided by this thickness of this n minus layer. So in case of SCR, from the device's point of view, what are the things that we need to remember on high level? Anyhow, point by point we already discussed in the video. So first thing is static IV characteristics. Okay, so what are the important terms that we need to highlight from that? What is SCR behavior in forward bias condition? What is SCR behavior in the reverse bias condition? And when the device is required to turn on, what is the important parameter? That is latching current. And in order to turn on the device, what are the gate characteristics? That is a second important characteristic. During the turn off process, what are the important terms? So from this diagram, IV characteristics, you can have that understanding. Now what are the important points that we need to take away from this? VBO. What is VBO? Forward forward breakover voltage. Okay. VRWM, this is a reverse breakdown voltage. And here important terms are, when gate current is not given here, if SCR is a forward bias, if you apply VBO voltage, then it will turn on. By applying a gate current, the turn on process will take place at a quite lesser values. Okay, latching current is one important parameter and holding current is important parameter during turn off process. These are the things we need to remember for SCR topic. Okay. Now what are the different methods to turn on SCR? Forward voltage triggering, gate triggering, and dV by dt triggering, and temperature triggering, and light triggering. Okay, light activated SCR. So in order to understand the turn on mechanism of SCR properly, we discussed or we used a 2 transistor model. Okay, so this 2 transistor model will tell you that anode current can be increased, one parameter by increasing gate current, another parameter by increasing leakage current. Okay, so the concept here is, by giving a gate current, so in this 2 transistor model, what will happen? So the regenerative process will establish, so that once it entered or crosses the latching current, it will continue its conduction. That is what we discussed. Okay, and these are the gate characteristics. Now in the switching characteristics of SCR, another 2 important terms are TQ, TC. For successful turn off, TC should be greater than TQ. for successful turn off, Tc should be greater than Tq. That is what we discussed. Why? Because by the end of Tq, device is not ready to block with the positive voltage in the next cycle. In order to avoid that, we should start the next cycle only after stored charge in J2 is completely removed off. That is what we discussed. So this is about SCR switching characteristics and gate characteristics. So we need to design a gate drive circuit in such a way that operating point is within this window. Okay, operating point is within that window. So this is a generally present days what types of triggering circuits are using here. In this particular circuit diagram, the important thing is there is a pulse transformer here. This pulse transformer will be operated with a high switching frequency, and in this particular switch, fast switches will be preferable like MOSFETs. And for this pulse transformer, the material is a ferrite core. Okay, the material is a ferrite core. After then, we discussed about a heat sink and series parallel connection of thyristors. Particular to this GATE exam, it's not so much important topic, but for ESE exam, this is an important topic. After this, we discussed in the video class, we studied about Snubber design and what are the limitations in case of SCR. Okay, so SCR is able to turn on with the gate current, but it is not able to turn off with the gate current. In order to overcome that, the next concept is GTO. The primary constructional difference between SCR and GTO is in case of GTO, gate cathode construction was divided into various modules. Okay, because of that, the negative gate current in GTO device is successful in turning off the device. Okay, that is the basic idea here. So this is a constructional diagram of GTO. What is the difference here? Gate cathode cross section is divided into various modules, and in GTO the important term is turn off gain. Okay, beta off, alpha 2 by alpha 1 plus alpha 2 minus 1. Okay, next this is the constructional diagram of a power MOSFET. This is a constructional diagram of a power MOSFET. So this is a drain, source and a gate. Due to this metal oxide gate oxide layer, input impedance is very high in case of MOSFET. Another important point here is MOSFET and IGBT comes under voltage controlled devices. Okay. Anyhow, in case of MOSFET, we may not get any questions on this device physics, but in which region it will operate as a switch, in which region it will operate as a turn on switch and a turn off switch. That is important thing. And we can expect here how to calculate these power losses in case of MOSFET. In MOSFET, during conduction state, it is modeled with equivalent on resistance. Okay, therefore we should calculate RMS value of the current waveform. During the switching transitions, MOSFET can be modeled as a capacitor. Okay, during switching transitions, MOSFET is modeled as capacitors. These are different switching models of power MOSFET. Now in IGBT, okay, in IGBT, what I am telling here, if you see the construction, the important thing here is this buffer layer. If this buffer layer is present and absent, what is the corresponding IGBT is called. Okay, so if without buffer layer, that construction is called non-punch through or symmetrical IGBT. This time this is one of the important word. Till now, they didn't use this terminology in the GATE exam. We may expect. Okay. Now, if buffer layer is present, IGBTs with buffer layer is termed as punch through or asymmetrical. Symmetrical non-punch through, asymmetrical punch through. Okay, they can means punch through devices can block only one polarity of the voltage. Non-punch through or symmetrical devices can block both the polarities of voltage. Okay, so and IGBT IV characteristics almost similar to that of BJT and but BJT, MOSFET, IGBT, these three devices comes under transistor family devices, but MOSFET will operate as a turn-on switch in ohmic region. BJT and IGBT will operate as a turn-on switch in the saturation region. That is one of the key point we need to remember here. So this is about IGBT quick revision. Again I am telling device physics is not prime criteria in this subject. So first chapter, what are the important things that you need to revise thoroughly? Fourier series, switch loss calculations, types of switches, coming to SCR characteristics, some gate drive problem calculations, and how to find for different latching currents, what are the different conditions. You go through the problems. Okay. So with this I will conclude first chapter revision, and in the next video we will go through second chapter revision plan. Thank you. Hello everyone. Now let us look into the second portion of revision plan. In the previous video we discussed about the revision plan for chapter 1. Now in this video let us look into the revision plan for chapter 2, that is basically rectifier analysis. So if you recollect from our earlier course videos, before starting the rectifiers we had defined overall converters one by one. Okay, so these are the different converter circuits we have. So the first one is AC to DC converters, that is basically a rectifier circuit. The second one is DC to DC converters, we can also call it as choppers and SMPS. Of course SMPS topic is not in the syllabus. And third one is DC to AC converters, that is inverter circuits. Fourth one is AC to AC converters. Okay, so from these converter analysis, the basic idea is all converter analysis mainly based on the waveforms of AC and DC. Okay, now if you see here, ideal AC waveform is sinusoidal, and one non-ideal waveform if you consider, that is for example a square waveform, we will notice here non-sinusoidal waveform will have harmonics. Okay, that harmonics conclusion we will get it through Fourier series analysis. Okay, so if you write down RMS value for this particular square waveform under a harmonic environment, what you need to write? Sum of squares of RMS values of individual components. In that, x1 is the fundamental component, that is a useful thing. x3, x5 and so on, those are all harmonics. Okay, so if you extract harmonic content, how can you extract that harmonic content? Under root xr square minus x1 square. If you evaluate that harmonic content as a ratio of fundamental component, such a ratio we can call it as a total harmonic distortion. Remember, whenever you come across non-sinusoidal AC waveform, then the important parameter of interest is total harmonic distortion or distortion factor. Okay, both are interlinked. So these two factors will give you what is the harmonic content and what is the fundamental component and what is the overall RMS value. So for non-sinusoidal waveforms, these two parameters THD and DF are important requirements. Now coming to DC waveform, here one example DC waveform, of course we can say this is pulsating DC. This is a pulsating DC. So this pulsating DC contains ripple component. You can also say that ripple component is nothing but RMS value of harmonic component. So that component, when it is expressed as ratio of useful component in this DC waveform. What is the useful component in DC waveform? That is nothing but average value. Okay. So that ratio is known as ripple factor, or RMS to average ratio is called form factor. Therefore, throughout the converter analysis, what are the parameters that is a more interest for us? That is THD and distortion factor in case of non-sinusoidal AC waveform, ripple factor and form factor in case of DC waveform. Okay, these are the important things before you starting converter analysis. Okay, now after that, now we can start AC to DC converters. At the first step of rectifiers study, we had classification. Okay, we had a classification. So this classification is done based on the control properties. Okay, so what are that? Uncontrolled rectifiers, fully controlled rectifiers and half controlled rectifiers, and they are further classified depends on the source. Okay, single phase and three phase. Here also single phase and three phase. Depending on the topology, half wave, full wave and center tap and bridge configurations in case of full wave. Similar classification is there in fully controlled and three phase also. Okay. Now another variety of rectifier circuits, that is half controlled rectifier circuits. Okay. Half controlled rectifiers also known as semi converters. Half controlled rectifiers also known as semi converters. There is one specific property of semi converter, that is a three phase semi converter. The number of pulses in three phase semi converter will be 3 and 6. So anyhow, in the three phase rectifiers we'll discuss that again. Okay. Now not only rectifier circuits, whenever you are analyzing any particular system as a theoretical understanding, first we will have some sort of assumptions. Those assumptions just to make the concept to be clear, right? Now coming to reality, there will be some non-idealities, we will relax those conditions. Okay. So for rectifier circuits to analyze, what are the basic assumptions? One is source voltage is assumed to be pure sinusoidal. Strictly speaking, the power system, sinusoidal voltage source may not be available due to several issues, but in order to make the rectifier concept to be clear, we will assume that source voltage is pure sinusoidal. Devices are assumed to be ideal. Okay, so we know that ideal devices will not be there, but just to simplify the discussion, we'll assume the devices are ideal. Transition times are neglected. Okay, but we know when we use diodes or thyristors in case of rectifier analysis, they will have some switching times, because these devices are classified under minority carrier devices. They will have some storage times. So whenever a device is trying to turn off, the charge stored in the device requires some time to turn it off, okay, or remove it off. So those times are neglected just for simplification of analysis. Okay. So before starting the rectifiers, always have in the high level what are the different types of rectifiers. Our rectifier analysis started first single phase half wave rectifiers. Single phase half wave rectifiers, second stage single phase full wave rectifiers, third stage three phase half wave, fourth stage three phase full wave. Different types of loads, different conditions we discussed with the waveform analysis and lot of mathematical equations. And remember, at least I expected by this time you should have your own revision tables of various formulas. If you don't prepare that, at least after this revision video, you make a small notes in the sense tables, just to for each circuit I will tell you what formulas are more important, I will round it out. So at least you capture those formulas and write it down on separate small very pocket type of notes. So these are very useful for very quick revision before exam. Okay. Now first what we discussed, single phase half wave uncontrolled rectifier. Okay, single phase half wave uncontrolled rectifier. So in this case we discussed with different types of loads. Okay, so for every circuit few things are compulsory. You have to, whether you have to memorize these formulas or on the spot draw the waveform and derive the equations. It depends on your level of practice. At least you should know what is the expression for average output voltage, what is the expression for average output current, and sometimes definitions for P naught. P naught definition, remember, it depends on the load property. Suppose if it is a SCR, another important parameter that will come across is a circuit turn off time. At least few basic information. Of course depends on the circuit and the load, some more additional parameters will come out. Okay, so we'll see all the parameters one by one. It's a quick revision. I am not going to draw any more waveforms on the board. These are already explained. If I started drawing all those things again, it will be repetition. Okay, this is not a repetition class, it is a revision class. So first what we considered was a resistive load. Okay, resistive load with a diode, So what waveforms we have plotted here? Output voltage, output current and voltage across diode waveform. So when the sinusoidal source is given to this rectifier circuit, we know that diode will be in conduction from 0 to pi. So diode will conduct from 0 to pi, hence output voltage is same as that of source voltage. So V0 waveform and I0 waveform. So in this particular case, as the load is a resistor, I0 waveform simply follows V0 waveform. Only difference is these magnitudes, okay, peak values. But these two waveforms will have peak value at same instant. These two waveforms will have peak value at same instant. So what are the few important things that you need to memorize here? Peak inverse voltage. Okay, it is same as a source voltage magnitude. Average output voltage. See, my sincere suggestion is, if you remember average output voltage formula by just looking at the circuit diagram, it is well and good. There is no need of worrying anything. Suppose if you forget this formula, okay, of course for diode and resistive load, this formula is very simple. If any specific different case is given in the exam, it is quite recommended that draw the waveform as a rough sketch. At least you learn how to write down this integration. Okay, If you are able to draw output voltage waveform from the given condition, and if you are able to write down this equation, you can get average output voltage or RMS output voltage, depends on the given question. But you should be confident enough to produce the waveform first, and how to write down the integration. If you practice these two conditions, these two things, then you can get correct answers. Okay. So now resist to load, average output current, you can simply write down I naught is equal to V naught by R. Once you are able to draw this waveform, it is not difficult to express RMS voltage. Okay. So RMS voltage, just mean of the square of the function. As the function is present only from 0 to pi, then integration is like this. Okay. Therefore, we will get RMS output voltage is equal to Vm by 2. For resistive load diode circuit, it is a quite simple. It's not so much difficult. Okay. Now, let us move to the next circuit. Diode circuit with pure inductor load. It is one of the important question, right? So we know that inductor property. What is inductor property? If inductor is subjected to positive voltage, current will increase. How it will increase? It depends on sourcing function. Suppose if it is a constant voltage, the current increasing will be in the form of a linear, a straight line with a slope of mx function. Suppose if it is having sinusoidal function, just simply write down KVL and solve it. You will get the solution for current. So in this particular case, we will get expression for current. Okay, we will get expression for current is I naught is equal to Vm by omega L multiplied with 1 minus cos omega t, simply by writing KVL, and we will get that one. So if you plot waveform for this equation, it will be something like this. It is like this. Now here at omega t is equal to pi, inductor current is at maximum, right? Therefore, it will require some other time in order to release that energy. Okay. So in case of pure inductor load, and pure sinusoidal source, what was our discussion in the regular classes? How much time inductor takes to store energy? It will take the same time to release that energy. In this particular circuit, as there is no resistor, there is no dissipating element, therefore storage and releasing intervals are equal. Therefore, inductor takes 0 to pi for the storage of energy. Therefore, it will take the same amount of time in order to release that energy as well, that is from pi to 2 pi. Okay. So in this particular waveform, what are the important points that we need to take away? One of the important point is average output voltage is equal to 0. Okay. What is the reason for that? Because the load is pure inductor. As per old second balance, in steady state, average voltage across inductor is 0. Okay. Average output current I naught is equal to Vm upon omega L. If you integrate this one, you will get that. And RMS output current. Remember, these two formulas are important not only from power electronics. These are important from measurements chapter also, measuring instruments. Okay. Why? There is a PMMC meter and EMI instrument. Okay. So accordingly we can frame the relationships. Okay. So pure inductor load is simply a hypothetical load, but coming to the practical case, there will be some resistance included. So when resistance was not there, what was the concept in the previous circuit? storage time and releasing time for an inductor energy are same. But because of this resistor, storage and releasing intervals could be different. Okay, how it is? The current waveform is something like this. Remember, this current waveform is non-sinusoidal. Okay, this current waveform is a non-sinusoidal. What is the reason for this current waveform to be non-sinusoidal? So reason is, when you are writing KVL, when the diode is on, this is what? KVL. It's a first order differential equation. If you solve that first order differential equation, the solution is in this form. Okay, the solution is in this form. Now if you observe this equation term by term, there are two important components here. One is sinusoidal component, another is exponential component. If you draw the combination of these two terms, okay, if you draw combination of these two terms, then I0 waveform will be non-sinusoidal like this. What is the important point in understanding this waveform? That is, yet omega t is equal to pi here. Okay, yet omega t is equal to pi. Current waveform magnitude is not equal to 0. Therefore, what is the consequence? When current is not equal to 0, okay, diode is not turned off because some current is flowing through the device. Diode is not turned off. When the diode will be turned off? The moment when this current reaches to 0. Because of that inductor, current will reaches to 0 only when the storage of energy completely releases. But due to the resistance in the load, storage of energy and releasing of energy will have different intervals. That is why this current reaches to 0 not at 2 pi. It reaches to 0 before that. That is at beta. Okay. So till this beta, current is flowing, hence diode is in conduction. Therefore, voltage across load will be followed by source voltage and the current waveform is like this. Now if you observe carefully here, from where to where diode is in conduction? 0 to beta. Okay, 0 to beta diode is in conduction, right? So what is the reason for that? Due to inductive property of the load. So in this waveform or in this circuit, what are the important terms that you need to remember? So those are average output voltage expression, okay, and conduction angle of the diode, right? And of course, if you remember, we might discussed this beta concept based on volt second balance equation. If you really want to get beta expression numerically, then what you have to do? We need to substitute omega t is equal to beta in I0 equation and equate to 0. Okay, then it will give you a transcendental equation something like this. Of course, strictly speaking, we need to solve this equation by using numerical methods. Okay, anyhow, I don't expect that type of question in the power electronics subject. So till now we discussed about resistive load, pure inductive load and RL load. Okay, so at this stage my sincere suggestion, just frame one table for different parameters from these three cases. Okay, so in these three cases, by looking into output current waveform, we can have some conclusions, right? The load current will be continuous and discontinuous. Okay, if load current having zero interval for a finite time, okay, zero value, I0 is equal to 0 for a finite interval, such load current is called discontinuous load current. If it is non-zero always, okay, always a finite value, then it is called continuous load current. Now you recollect, suppose if the load having a DC motor and load current is of discontinuous nature, okay, so it is quite difficult to operate a DC motor type of loads with a smooth speed because of discontinuous nature. In order to minimize the vibrations in the speed, what is the common practice? The common practice is load current continuity behavior should be improved, okay. That can be achieved by placing freewheeling diode across the inductor load, okay. What is the concept of freewheeling diode? Whenever inductor load current has discontinuous behavior, if at all the load is a DC motor type, smooth speed control is highly difficult to obtain, okay. To achieve this objective, what is the common requirement? Load current waveform has to be improved towards a continuous behavior. In order to achieve that, a freewheeling diode will be used, okay. So at this stage you should understand what is the significance of freewheeling action. The freewheeling action will improve continuity behavior of load current and it will improve the input power factor, okay. It will improve the input power factor. So there are different names for freewheeling diode. It's also important objective question. Flywheel diode, feedback diode or commutating diode. These three are other names for freewheeling diode, okay. Next, now let us look into another category, RE load. Remember, for RE load, basic practical example is a battery charging circuit. Here also I0 waveform is discontinuous. I0 waveform is discontinuous, okay. So in this particular circuit, what are the important parameters that need to be remembered? Now in this particular circuit, average output current is the first point of interest. From then you can calculate average output voltage, okay. So once you have V0 and I0, average output power can be calculated, but here RMS output current is a different term we need to calculate. So these things you can calculate just by this integration, and the waveforms for RE load will be like this. So what is the difference from RE load to previous resistor load? Remember, in case of resistor load, this current directly started from 0, but because of this resistor load, RE load, the battery at the load side, diode will start conduction from the instant at theta here. What is the instant theta? That is the instant where source voltage and load EMF both are equal. After that instant, diode started conduction, okay, because sinusoidal value is higher than the load EMF. So in this particular example, diode will be in conduction from theta to pi minus theta, okay, theta to pi minus theta, and peak inverse voltage is here, right, peak inverse voltage is here. Now this is about RE load. So I hope you might completed these skill assessment problems. So in this particular case I gave LE load, right. This is one of the interesting problem. I hope you might completed this. So find the expression for I0, small I0. Only simple thing is you just write down the equation for when the diode is on, you just write down KVL, L into d I0 by dt plus E is equal to sinusoidal source. Sinusoidal source. If you solve this equation, you will get an expression for I0. That is the first order differential equation. So one hint I can tell you here, I naught waveform will have maximum value at pi minus theta. Okay, try to figure out the reason. I naught value has peak value at pi minus theta. Okay, so these are different cases about diode rectifier and resistor load. Just I am again a quick revision. Single phase half wave diode rectifiers. What are the different circuits or cases? R load, pure inductive load, RL load, RE load. Okay, LE load and capacitor load are the problems. Just remember in what way, in the what sequence our class has moved. If you just memorize that, even in the exam also it is easy to pick up. Okay, and if you refer different textbooks, of course person to person there will be different sequences. I am not questioning that sequence, but always you try to follow one sequence. It will be easy for memory. You would tune your mind in one particular sequence so that you can avoid the confusions. After that, the next category is single phase half wave phase controlled rectifier. So if you understand the diode sequence, with the same sequence here also you can have. But what is the difference in this particular case? Now the device is SCR. Okay. Now the device is a SCR. Here also what is the order? You need to recollect average output voltage, average output current, RMS voltage depends on the given situation. R load, RL load, pure inductive load, RE load, RLE loads. Okay, RLE loads. So that is the sequence. If you remember that, then it is well and good. Okay. Now let us look into the waveforms quickly. So for resistor load, these are the waveforms. What is the basic concept here? What is the new parameter in these waveforms? That is alpha, right? In the original circuit here, in the original circuit diagram, gate drive circuit is not shown. Okay, gate drive circuit is not shown here. Gate drive circuit is not shown. But there is a gate drive circuit between gate and cathode terminals. That circuit will identify at what instant the source voltage has, zero crossing. At what instant the source voltage has a zero crossing. So from that instant it will convert our firing angle requirement from angle into time. For example, we need to trigger the SCR at omega t is equal to 45 degree. Depends on the sinusoidal source frequency, that 45 degree will be converted into equivalent time. At that particular instant of time, it will produce a small firing angle. Okay, accordingly the device will be turned on. Now in this particular circuit, SCR will be in conduction from alpha to pi after receiving the firing angle. Okay, so output voltage will be same as source voltage from alpha to pi. As the load is resistor, output current will also simply follows output voltage. Okay, so from 0 to alpha here, 0 to alpha, SCR is in forward blocking state. Alpha to pi, SCR is in conduction interval, hence voltage drop across SCR is a 0 here. Okay, and pi to 2 pi plus alpha, SCR is in the blocking state, out of which pi to 2 pi it is a turn off interval, 2 pi to 2 pi plus alpha it is forward blocking interval, right? Therefore pi to 2 pi should be treated as circuit turn off time. Now this particular circuit turn off time, if you convert it into equivalent time interval from the source frequency, that particular TC should be greater than device turn off time in order to have successful commutation. Okay. Now let us look into what are the equations to be important here. Obviously, as I told, average output voltage one important expression to remember. Circuit turn off time omega Tc is equal to pi radian or Tc is equal to pi by omega radian. Another thing is RMS output voltage. So if you understand how to draw output voltage waveform, RMS calculation is very simple. So here you can write down RMS output voltage is first integration. If you simplify, you will get an expression like this. Another important expression in this particular circuit, that is input power factor. Okay, input power factor. Now from this expression, what is important point here, if firing angle increases, okay, input power factor will decrease. That is one of the basic drawback of phase controlled rectifier circuit. Now this is about resistive load. Now if you look into the next case, that is a inductive load. I will quickly show the inductive load circuit diagram, RL load. So same circuit was there earlier with a diode. Now this is with a thyristor. What is the difference in this solution? Now this is the solution for current flowing through the circuit. The term different here is this particular term has alpha. Okay, this particular term has a alpha. If you substitute alpha is equal to 0, SCR circuit is equivalent of a diode. You will get back the previous circuit. Okay, sorry, previous equation. So equations wise both are same structure, and in this particular circuit SCR conducts from alpha to pi, and hence this is the integration, so that output voltage expression will be like this. So wherever I am writing your circles, you try to capture those formulas and you write it down in a separate paper, so that it will be the point of interest in these circuits. Okay. Now these are the waveforms. So in this particular waveform, SCR will be in conduction from alpha to beta. Here alpha to beta, SCR is in conduction. So output current will have sinusoidal and exponential behavior. So in that interval, load will be connected to source voltage. So V0 will be same as source voltage. Okay. And what is the next case? Of course, here also beta calculation is by using this numerical method. What is the next waveform? This is a pure inductive load. This is a pure inductive load. So in pure inductive load, just like a diode, what is the difference here? The difference is, in case of diode, I0 started from 0, but now it started from alpha. That is the only difference. Therefore, how much time inductor will store energy? That is from alpha to pi. So it will store energy for a period of pi minus alpha. Okay. So how much time it requires to release that energy? Another pi minus alpha. Therefore, this is what conduction interval. Okay. So in this particular case, alpha to pi, inductor will store energy. Pi to 2 pi minus alpha, inductor will release energy, and hence volt second balance equation will satisfy, and solution from KVL will give you I0 is equal to Vm upon omega L cos alpha minus cos omega t. Okay. Now the next circuit is RE load. RE load. In this particular circuit, what is the basic condition for SCR to be turned on? That is, alpha, this one, alpha should be given after theta. Okay, alpha should be given after theta, so that SCR will be started conduction. For example, in this particular circuit, one special case is If thyristor is turned on or triggered continuously with a constant DC signal, then in such cases alpha value will not be provided. In such cases you can safely take alpha is equal to theta. But in this particular case, general case is alpha should be greater than or equal to theta. Okay. So SCR will be in conduction from alpha to pi minus theta. So in this interval alpha to pi minus theta, device will be in conduction. Pi minus theta to 2 pi plus alpha, device is in the blocking state. Out of that, up to 2 pi plus theta, SCR is in completely in the turn off state. Okay. Therefore, what could be the circuit turn off time? Here this is a theta interval and this is pi interval and this is a theta. So if you take this total, pi plus 2 theta will give you the circuit turn off time, and remaining expressions are same as diode circuit. I0 expression, average output current, is important thing here in this particular circuit, and rest all the equations are just similar to diode circuit. Okay. So don't scare to memorize this lengthy formula. Mostly in GATE exam, such lengthy memory based questions will not be asked. Okay, no need to worry about it. But a concept learning we already discussed and did some numerical examples also in the regular course. Okay. Now coming to the next category, that is RLE load. What is the physical example for this RLE load? That is a DC motor. Okay. So where EMF term in that RLE load, you can simply say that is a back EMF in case of DC motor, right? So in this particular circuit, output current equation has, just like earlier, here also it will have sinusoidal and exponential term. Again, don't worry to memorize this equation also. This equation is to understand to explain the waveform shape of this I0 waveform. Okay. So from this case you can understand device will be in conduction from alpha to beta. Therefore, alpha to beta, when device is in conduction, output voltage will be same as that of source voltage. Okay. And device is in the turn off state from beta to 2 pi plus alpha. So in this interval. Okay. So in this interval, device is not in the conduction state. However, device will be considered as under completely turn off state up to 2 pi plus theta. Okay. Therefore, circuit turn off time will be treated from beta to 2 pi plus theta. So this is about RLE load, and what equations that is important for our exam, that is V0, average output voltage expression, is important for us, and average output current I0 is equal to V0 minus E divided by R. So with this stage we just quickly revise single phase half wave rectifier. Okay, single phase half wave rectifier is quickly revised. Okay, diode circuit and with thyristor, right? So in this particular circuits, what are the important things? R load, pure inductive load, RL load, RE load, and RLE loads, right? So on high level, these are the things that we need to remember. Okay. Now when you talking about half wave rectifier circuits, one of the important aspect is, for half wave rectifier circuit, not only half wave rectifier, for any rectifier circuit, source will be taken from secondary of some transformer. What do you mean by that? IS is the same as secondary current of a transformer. Due to presence of this diode at the secondary side of the transformer, one half cycle is missing. That means secondary current have DC component. Secondary current have DC component. So because of this DC component, source transformer is moved towards saturation. Because of that, half-wave rectifier circuits are not advisable to use in very high power applications. In order to overcome this problem, we need to go with the full wave rectifier circuits. That is the basic introduction we have given in order to start full wave rectifier circuits. Now, there are two basic concepts in order to understand full wave rectifier circuits. What are that? One is common cathode configuration, another is common anode configuration. So, in this particular circuit, the device which is connected to higher positive potential will conduct. In the common anode configuration, the device which is connected to higher negative potential will be in conduction. So with this concept, we discussed full wave rectifier circuits. Okay. Now in single phase full wave rectifier circuits, there are three major categories. One is full wave rectifier, full converter that has two circuits. One is a midpoint converter and another is full converter. The second one is single phase semi converter. What I mean by three circuits: single phase, midpoint converter and full converter and semi converter. Semi converter has further three topologies, right? Symmetric, asymmetric and single phase full converter with a freewheeling diode, right? Now, while studying this full wave rectifier circuits, we had few assumptions first. What are these assumptions? The common statement from all of these points is load current is continuous nature. Continuous nature is possible when the load is having sufficiently large inductance. So when you are doing problems in the exam also, make sure that whether load current is continuous condition is given or discontinuous condition is given. Do not jump with the ready-made formulas. Okay. So before applying any formula, you be careful. Just make sure whether it is a continuous or discontinuous. And rest of the explanation is quite simple. Now here there are two devices. One is a T1, another is a T2. What is the basic concept here? T1 will conduct when VAO is more positive. T2 will conduct when VBO is more positive. Now, let us see that. Suppose due to the center tap connection, the source voltage, that is VAO, is positive from 0 to pi and hence T1 can be conduct, and VBO is more positive from pi to 2 pi. Therefore, it is possible for T2 can be conducting. So when T1 is conducting, this is the equivalent circuit. When T2 is conducting, this is the equivalent circuit. Okay. Now, whenever T1 is on, that is from alpha to pi plus alpha, output voltage will be same as source voltage. Whenever T2 is in conduction, output voltage will be same as, again here also, source voltage. But what is that source? V0 is equal to VAO. V0 is equal to VAO here. When T2 is on, V0 is equal to VBO. Therefore, alpha to pi plus alpha, in your output voltage waveform, we will have VAO waveform, and when T2 is on, pi plus alpha to 2 pi plus alpha, V0 will be same as a VBO. Okay. So corresponding waveforms looks like this. Okay. Now in this particular circuit, another important parameter is peak inverse voltage of device rating, that is 2 times of the source voltage, okay. And in this waveform the important parameters are average output voltage, circuit turn off time and peak inverse voltage. These three are important things in order to understand a single phase midpoint converter. What are the drawbacks here? It requires center tap transformer and PIV rating of devices will be high. These two drawbacks can be overcome in case of full converter. These drawbacks, it can be overcome in single phase full converter. The key points to analyze this circuit that is T1 and T3 upper half devices with odd number notation, they are connected in common cathode configuration. Lower half devices T4 and T2 are in common anode configuration, okay. Lower half devices T4 and T2 are in common anode configuration. Now, if you recollect common cathode and common anode configuration, common cathode, the devices which is connected to higher positive potential will be in conduction. Therefore, T1 can forward bias, okay, whenever terminal A is more positive than terminal B. Similarly, T3 can forward bias if B is more positive than terminal A. In the similar way, you can interpret for common anode configuration. So, according to that, alpha to pi alpha to pi T1 and T2 devices are in conduction, pi plus alpha to 2 pi plus alpha T3 and T4 devices are in conduction, okay. Now, by using this, we will get output voltage waveform something like this. When T1 and T2 pair is in conduction here, output voltage will be followed by VBA in this interval, okay. When T3 and T4 devices are in conduction, that is from pi plus alpha to 2 pi plus alpha, then output voltage will be followed by VBA, okay. That is a red color sinusoidal waveform. Now, we assume that load current is a constant here. We assume that load current is a constant here. Now, this waveform, this particular waveform is when alpha is greater than pi by 2. Now, what is the important point that we need to compare these two cases? When alpha is less than pi by 2, majority of V0 waveform is in the positive side. Okay. Now, if you observe here, majority of V0 waveform is in positive side. Therefore, you can say average output voltage is positive. But when alpha is greater than pi by 2, majority of V0 waveform is in the negative side. Hence, average output voltage is negative. Hence, we can conclude this is rectifier operation, okay, and this is inverter operation. Remember, single phase full converter circuit can operate as a rectifier when alpha is less than pi by 2, operate as an inverter when alpha is greater than pi by 2. In this particular aspect, there are some questions also, previous GATE questions. Recent engineering services exam, 120 marks conventional question also given on this particular aspect, okay. Now, okay, in order to understand the source current waveform, if you go back and see the equivalent circuits, this particular one, when T1 T2 pair is in conduction, the source current, or if I draw the direction of the current, will be something like this. This is the direction of the current. this particular direction of the current is same as that of original reference direction. Hence, you can conclude source current is positive here. Okay. Now, suppose if T3 and T4 pair is in conduction, this is what the direction of the current. In that case, source current direction is opposite to reference direction. From these conclusions, you will get source current waveform as a square waveform here. Source current waveform as a square waveform. So in this particular square waveform, if you recollect from first chapter Fourier series equations, you will notice that peak value of this fundamental component is 4I0 by pi. 4I0 by pi. There is a lot of discussion on this particular waveform itself. Okay. Now, one important point here, why it is a very important, source voltage here, source voltage Vs is Vm sin omega t, but source current is non-sinusoidal. For this particular rectifier circuit, what is the source? That is nothing but a power system grid. Because of this a phase controlled rectifier circuit that is placed in the power system grid, source current contains Is. Is contains harmonics. Source current contains harmonics. This is a major issue in phase controlled rectifier circuit. What are those harmonics? If you look into Fourier series analysis, you can understand that one. Okay. So anyhow, these points are inverter operation. I already talked about it. Now, source current contains very important statement. All odd harmonics. You will come across a similar statement in three-phase rectifier also. At this moment, these are all odd harmonics. What is the lower order harmonic? That is a third harmonic. Lower order harmonic is a third harmonic. Okay. Now, in this particular case, what are the important parameters? RMS value of fundamental source current. Is1 is equal to 4 by pi I0 total divided by root 2. Will give you this number. RMS value of source current is equal to I0. Okay. And a displacement power factor. What is the reason for this displacement power factor? Now, in our power systems class, generally we will calculate power factor is equal to cosine of the phase angle between voltage and the current. But in this particular case, voltage and current are both non-sinusoidals. Only one waveform is a sinusoidal. Whenever you have a specific that particular case, you should express fundamental source voltage and fundamental source current. Power factor is defined between fundamental components of Vs and Is, that is known as displacement power factor here. Displacement power factor, that is a cos alpha. Okay, for this circuit. Now, distortion factor is defined like this: RMS value of fundamental source current upon RMS value of source current. Why we are interested to define distortion factor in the source current only? Because source current is non-sinusoidal waveform. That is the reason. Okay. So that value will come across 0.9. So once DPF and DF are defined, now input power factor is equal to TF multiplied with DPF. It is a very important conclusion in this particular circuit. Total harmonic distortion is 48.43%. This is another important point. Okay. So these are the things that we need to take away from single phase full converter. If you understand single phase full converter, and the next circuit that we can move, that is a semi converter. Semi converter circuit has three topologies. Okay, semi converter circuit has a three topologies. Now observe carefully here. Upper half devices both are thyristors. Okay, then it is a symmetric configuration. Lower half devices both are diodes. Okay, in asymmetric configuration, these two, one vertical section contains thyristor and this vertical section contains diodes. That is a asymmetric configuration. Next, for full converter, if you place a freewheeling diode, then it will also treated as single phase semi converter. So depends on the circuit operation. Anyhow, I just formulated this table, right? So according to that table or based on the waveforms also, you can get the waveforms are something like this. Okay, all the three circuits, these waveforms are applicable for three circuits, the three topologies of three phase semi converter. Okay, now observe carefully, whatever the firing angle you can consider, output voltage will be always in the positive side. Okay, and pi to pi plus alpha, it is freewheeling action. What do you mean by that? For any firing angle, for any firing angle, it will always give you first quadrant of operation. So first quadrant of operation means only rectifier operation. Only rectifier operation. Suppose if the load is a DC motor, first quadrant of operation is called forward motoring. Okay, first quadrant of operation is called forward motoring, right? Now in this particular circuit, in order to understand source current waveform, if you look into first and second position devices are in conduction, we will get source current is a positive here. So in this interval, first and second position devices are in conduction. During freewheeling action, source and load will be separated, hence source current will be 0. Now from pi plus alpha to 2 pi, third and fourth devices are in conduction, hence source current will be negative. So because of that, source current waveform, what is the waveform shape here? Quasi square waveform. Okay, waveform shape is a quasi square waveform. Again you can recollect from first chapter. Again you can recollect from the first chapter what is the peak value of that fundamental. Anyhow, we will see next. So depends on the table. For each configurations, you can draw T1 current, D2 current, means one thyristor current, one diode current. Okay, you will get a waveforms something like this. Now in this particular circuit, this is what I am telling. See, whenever first and second position devices are in conduction, the direction of current will be like this. It is same as the reference direction. In this interval, source and load, that is a freewheeling interval, source and load are separated. Hence source current will be 0. Now in this interval, this is how the direction of current is. Okay, So this current is opposite to reference direction, hence Is is equal to minus I naught here. So freewheeling action, source and load are separated, hence source current will be 0. So with this conclusions, we got source current waveform as a quasi square waveform. One of the important conclusion from this waveform is zero crossing of this particular waveform is at alpha by 2. Due to that alpha by 2, what parameter we can calculate? That is dpf cos alpha by 2. Okay, that is dpf cos alpha by 2, right? Now these are some of the useful terms that we need to remember. Source current expression here, and this is a input power factor expression. So dpf is equal to cos alpha by 2. Okay, in case of single phase full converter, that dpf was cos alpha. So for the given firing angle, we can say dpf of single phase semi converter is better than dpf of single phase full converter. Very important conclusion. And in this particular circuit, average and RMS values of SCR and diode currents for the three configurations. Okay, if you understand the waveform, you can calculate very quickly, right? This is about single phase semi converter. And the next discussion in our analysis is, now I will write down for the next two circuits in the high level. This is a discontinuous conduction. In this discontinuous conduction, we need to analyze the circuits for RLE load first, next RL, next R, and then RE loads. Okay. So these loads you need to analyze for single phase full converter, single phase semi converter, single phase semi converter, that is a high level. Okay. Now I am again repeating, single phase full converter, what was the analysis part? Midpoint converter and single phase full converter, single phase semi converter. Okay. Single phase semi converter has three topologies: symmetric, asymmetric, and full converter with the freewheeling diode. So full wave rectifiers means immediately try to have this type of classification: midpoint, full converter, semi converter. Now all of this discussion is for continuous conduction. All of this discussion is for continuous conduction. Coming to discontinuous conduction, this is the sequence. Okay, sequence is very important. Of course, in the exam, in the same sequence it will not be asked, but in your mind that sequence should be there. Okay, so for full converter, this page will give you waveforms for different cases. Okay, so these two waveforms are for RLE load. So in case of RLE load, alpha to beta device numbers 1 and 2 will be in conduction. Pi plus alpha to pi plus beta 3 and 4 devices will be in conduction. Okay, this is for RLE load. Now for RL load, what are the waveforms? These two are the waveforms for RL load. Okay. Now this is for resistive load both V0 as well as I0 waveforms. This is for RE load. So I hope if you relook or if you remember, then these are the waveforms, and you will have a same set of waveforms repetition for single phase semi converter circuit also. Okay. So you just remember the sequence: single phase full converter and single phase semi converter in discontinuous conduction. What are the loads we discussed? RLE, RL, R and RE loads, right? Now this total full converter analysis discussion was without source inductance part. Now another case is when source inductance is considered. When source inductance is considered, there is a slight difference in the analysis. Now see here, when inductance is not considered, this overlap angle will not come into picture. Whenever source inductance is considered, see, without source inductance, that was the waveform. When source inductance is considered, this particular waveform is removed. Okay. Due to that, there is some reduction in the output voltage. What is the reason for that one? Because when source inductance is considered, there will be some overlap between the pair of devices. So during that overlap interval denoted with the symbol mu, when all the four thyristors are in conduction, output voltage will be 0, right? And hence there will be some reduction in the output voltage. So because of that, source inductance, now observe carefully here, source current waveform is modified to trapezoidal waveform. Okay, trapezoidal waveform, right? Now in this case, source current fundamental component crosses x-axis at this point. Therefore displacement power factor will be this one. Displacement power factor will be cos of alpha plus mu by 2. Now when source inductance is considered, average output voltage will be less than the previous equation, that was 2 Vm by pi cos alpha. It will be subtracted by some number. Okay, this one is the average output voltage equation. Now observe carefully here. This is the expression for average output voltage. Now the second term is the reduction in average output voltage due to source inductance. This 2 is very important here. Okay, that 2 is very important here. At this particular stage, I would like to stretch one point. In PS Bimbra textbook, that 2 is not there. Okay, but in some foreign other standard textbooks, 2 is there, and even there is one previous GATE question also, answer was given based on 2 is considered. Okay, so you please note down here this 2 is present, right? So that is the expression for average output voltage when source inductance is considered. In order to find overlap angle, we can use this equation. This equation got derived simply by writing KVL during the overlap interval. Okay, so I think with this single phase full wave rectifier is revised quickly. Another important point here is voltage regulation is given by this one. For example, if the circuit is given as diode rectifier, okay, in case of diode rectifier you have to substitute alpha is equal to 0. In that case it will be, the expression could be like this: 1 minus cos mu divided by 2. 1 minus cos mu divided by 2. In case of diode circuit, this voltage regulation formula, it will be modified like that. Okay. So with this, single phase rectifiers completed, and please do all of these skill assessment problems. These are very interesting problems. Now the next topic is three phase rectifier circuits. What is the motivation to start three phase rectifier circuits? In case of single phase rectifiers, we discussed output voltage waveform will have two pulses in the load side, maximum two. Half wave rectifier 1, full wave rectifier 2. Source current has all odd harmonics. So whenever output voltage is having a ripple component, that ripple can be minimized by increasing the number of pulses. In the source current also, some of the some of the odd harmonics can be eliminated by operating the converter circuit with more number of pulses. This can be possible if you use a three phase rectifier instead of single phase rectifier. So before starting three phase rectifier circuits, what are the two basic things that you need to remember? Expressions for phase voltages, expressions for line voltages, and keep this phasor diagram in mind. Okay. So from this phasor diagram, what is the takeaway? Phase angle between VAO, VBO and VCO is 120 degree. Phase angle between line voltages AB, BC and CA is also 120 degree. Phase angle between one line and one phase voltage is 30 degree. How it is? VAB leads VAO by 30 degree, leading. So based on this particular aspect, in the analysis part there is a slight differences. Again I will highlight that. Now these harmonic numbers, 6k minus 1 harmonic numbers, will introduce negative phase sequence. If the fundamental phase sequence is ABC, phase sequence due to 6k minus 1 harmonics is negative ACB. Okay. If the fundamental phase sequence is ABC, phase sequence due to 6k plus 1 harmonic is that is 7, 13, 19 is the same ABC only. Okay. So 6k minus 1 harmonics will introduce negative phase sequence, 6k plus 1 harmonics will introduce positive phase sequence. Okay. So negative phase sequence or 6k minus 1 harmonics are more dangerous in three phase. Now what are the first step in the three phase rectifier analysis? Common cathode and common anode configuration. So what we studied earlier, half wave rectifier circuits are preferable to analyze with phase voltages. Half wave rectifier circuits are preferable to analyze phase voltages. Okay. So here D1 will be in conduction when phase A voltage is more positive. In that interval V0 is equal to VAO. D3 will be in conduction when phase B voltage is more positive. In that interval V0 is equal to VBO and so on. Now if you look into source voltage waveform, okay, if you look into source voltage waveform, this source voltage waveform is drawn based on phase voltage as reference. Okay. Now VAO is more positive from this point. This is a 30 degree point and this is 150 degree point. Anyhow, it is written here. Okay. So from 30 to 150 degree, VAO is more positive. The device placed in VAO, that is D1, will be in conduction. 150 to 270, that is here. Phase B is more positive. In that interval, D3 will be in conduction. Similarly, 270 to 390, phase C is more positive. In that interval, D5 will be in conduction. Okay. So, if you draw the respective waveform shapes at the load side, output voltage will be like this. If you consider load is a resistor here, output current waveform simply follows output voltage. For current stiff load, load current is always constant. Okay. So, at the time of integration, how can you define average output voltage? First, you should take the periodicity. What is the periodicity? 2 pi by 3. Pulse is repeating at an interval of 2 pi by 3. How to define this pulse limits? Pi by 6. Okay, pi by 6 to 5 pi by 6. I think I wrote the integration here. So, V0 integration 1 by periodicity 2 pi by 3, integration from pi by 6 to 5 pi by 6. Then it will give you average output voltage V0 like this. Okay, that is the expression for average output voltage. Suppose if the load is a resistor, you simply same integration but square it. You will get RMS voltage expression something like this. Okay. Now, in case of common anode configuration, you will get the same waveform but in the negative side. Okay. So, the next circuit is earlier diodes. Now it is replaced with thyristors. Okay. Earlier diodes now replaced with the thyristors. There is no change in the source voltage waveform. Now this particular circuit is one important case, and mostly students will commit a mistake here. So for these circuits, alpha is measured from these points. What are these points? Are called positive phase crossover points, 30, 120 and 150. Okay. If alpha is equal to 0, output voltage is just same as that of a diode. There is no change. If alpha is if alpha is 15 degree, then the same waveform is just delayed by 15 degree, so that the limits here pi by 6 plus alpha to 5 pi by 6 plus alpha. Okay. So if I assume the load is a resistor, output current will simply follows output voltage. Therefore, I0 waveform again will be same as waveform number 2. Hence, we have not repeated even in the class also. Suppose if alpha is increased a little bit, that is let us say up to 30 degree, then what is the point of observation here? This V0 waveform simply touches x-axis. V0 waveform simply touches x-axis. Okay. Hence, V0 waveform looks like this. So you can treat this particular waveform as boundary condition. Okay. The previous two waveforms are considered as continuous conduction for a resistive load. In case of resistive load, if alpha is further increased, for example, if alpha is 30 degree, now observe carefully here, in this particular interval, there is a discontinuity. There is discontinuity. Okay. So, in case of resistive load, for 3-phase half-wave rectifier circuit, alpha less than 30 is equal to 30 and greater than 30. We should be very careful enough. correspondingly equations will also have different scenarios. Okay, suppose if the load is current stiff load, what waveforms are applicable? Waveform number 1, 2, 3 and 5 are applicable. In case of current stiff load, there is no discontinuity, just like earlier. Okay, so this is the waveform for alpha is equal to 60 degree. This is the waveform for alpha is equal to 60 degree for current stiff load. Suppose for that current stiff load, if we place a freewheeling diode across the inductor load, so this is also for alpha is equal to 60 degree, but this waveform is for current stiff load with freewheeling diode. Anyhow, I wrote all the points in detail in this particular notes. People used to say this is a short notes, but this is a almost a very detailed notes. I didn't miss any single point in this entire notes. So for resistive load, alpha less than 30 is equal to 30 greater than 30, continuous, boundary and discontinuous. For inductor load with I naught constant, okay, waveform numbers 1, 2, 3 and 5, right? Inductor load with the freewheeling diode, inductor load with the freewheeling diode. So these are the waveforms. Okay, now now these are the different equations that you need to remember. For alpha less than 30 degree, okay, don't try to memorize these formulas. Only thing you need to remember is this integration. Only thing you need to remember. Even if you understand the waveform, if you just able to write down that integration, you can easily simplify it, isn't it? So this is a RMS voltage equation. This is RMS voltage equation. Now what is my sincere suggestion is, by using these formulas you make your own table. So strictly speaking, I am not interested in this type of ready-made notes. If myself if I prepare these notes, most of the students will not write on paper, so they will not get practice. Of course, whenever you are seeing these equations and waveforms on the board, you will feel okay, fine, these are very nice, I remember, I understood. But coming to the exam, you have a difficulty. Okay, once exam is over, and if you're not writing and you are not preparing on your own, then you will understand. So don't do that mistake. So this revision is just to warn that type of mistakes in your preparation. Now for resistive load, when alpha is greater than 30 degree, what are the formulas are important? Average and RMS voltages. Okay. For current stiff load, equation is very simple, and current stiff load and freewheeling diode. See, these are not new equations. If you remember the previous equations, only thing is which equation to be applied. Okay, this is earlier equation only, this is also earlier equation only. Remember, in this half wave rectifier circuits, in all of these expressions, that value is VMP. Okay, in full wave rectifier circuit, you will have this value as VML. That is very, very important. Peak value of phase voltage. Next, this is about 3-phase half wave rectifier. The next one is diode rectifier. So diode bridge rectifier. Okay. In case of this diode bridge rectifier, the most important thing is if you observe output voltage side, we had a conclusions AB, AC, BC, BA. Therefore, line voltages at the source side is preferable for the analysis. Okay, line voltages at the source side is preferable for the analysis. That is, in order to explain that difficulty only, we took this waveform. Okay. So for 3-phase bridge rectifier circuits, line voltages are preferable. However, with this explanation, average output voltage equation is given by 3 VML by 5. Now by taking line voltages as a reference, by taking line voltages as a reference, we discussed this 3-phase full converter circuit. Okay, this 3-phase full converter circuit. Now in this particular case, the circuit is consisting of 6 thyristors. Load is assumed to be current stiff load. Now observe carefully here, these are line voltages. Source voltage is drawn based on line voltages. Okay, in this particular circuit, what is required here? In this particular circuit, what is required? Source current is one point of discussion. Source current is one point of discussion. Displacement power factor is one point of discussion when you are drawing a output voltage, different waveforms for various firing angles. Another thing is voltage across a particular device. Okay, now you just go through the waveforms. What is important here? This particular source voltage waveform is drawn based on line voltages reference. Now in case of diode bridge and this thyristor bridge, try to observe the difference carefully here. I will just go back to diode circuit. Diode circuit, D1 started from 30 degree. This is based on phase voltage as reference. This is based on phase voltage as a reference. But at the same place, thyristor is there. T1 is conducting from 60 degree. What is the difference here? Is it because of thyristors is used as devices? No. The reason for this difference is this waveform is drawn based on line voltages as a reference. Okay. So earlier in case of phase voltage source, whatever phase crossover point that is at 30 degree, now that point is moved towards 60 degree. That is the difference. Okay. So earlier D1 conducts from 30 to 150. So in this full converter circuit, when alpha is equal to 0 degree, T1 conducts from 60 to 180. If you understand this difference, these waveforms are nothing. Okay. So in diode circuit, when phase voltage is taken as reference, D1 conducts from 30 degree to 150 degree. For the same circuit with alpha is equal to 0, thyristor circuit is same as like a diode circuit with alpha is equal to 0. So in that case, what happened? T1 conducts from 60 to 180. That difference is because of line voltages are taken as a reference. Okay. So if you understand this conduction sequence diagram, correspondingly you will get output voltage like this. Now in order to draw source current waveform, now observe carefully here. Suppose if T1 is in conduction, source current will flow as per the direction shown in that figure. So I can write down here ISA is equal to plus I0 when T1 is on, minus I0 when T4 is on. Similarly, ISB and ISC. So when you are drawing a source current waveform, what are the key points? If the upper half device is turned on, that particular phase current is positive. If the lower half device is turned on, that particular phase current is a negative. Okay. Now, so with that explanation, we will get source current waveform as a quasi square waveform. Again, one more point here. Source voltage, it is a line voltage. VAB started at 0. corresponding source current started from 30 degree, isn't it? But in order to define DPF, what is the definition for DPF? Cosine of the fundamental phase voltage and fundamental phase current, angle between fundamental phase voltage and fundamental phase current. Take a cos of that, will give you displacement power factor. Hence, for alpha is equal to 0, the displacement factor will be 0 degree. Okay, like that, if you understand alpha is equal to 0 waveforms, those waveforms will be shifted by 30 degree, 60 degree, 90 degree and so on. Then you will get these are the different waveforms. Okay, again I will not go into point by point explanation. What are the important conclusions that you need to take away here? Here also, when alpha is less than 90 and greater than 90, so first quadrant operation is a rectifier operation, fourth quadrant operation is an inverter operation. Okay, source current waveform is a quasi square waveform whose Fourier series expression is given by this. Okay, now from this waveform you can say source current contains 6k plus or minus 1 harmonics, and peak value of fundamental source current is 2 root 3 by pi into I naught. Okay, for example, that value is here 2 root 3 by pi into I naught. Okay, now now these are some of the equations and important things. THD of source current 31.08%. Now in case of resist to load, this is another important condition. Alpha less than 60, alpha greater than 60 degree, continuous and discontinuous conduction. Now if you observe carefully here, V naught expression contains VML. Okay, this is a VML. In case of half wave rectifier, this number was VMP. Now this is a VML. Okay, so just by writing the integration and simplifying, we'll get these equations. So these all of these equations are important. Now the next circuit is from the 3-phase full converter. If you replace the lower half devices with diodes, you will get 3-phase semi converter. Here also the same exercise, it is the only thing is the laborious exercise. So you can have waveforms like this. So for alpha is equal to 0, conduction sequence diagram exactly replica of 3-phase of full converter. There is no difference. Hence V naught waveform also you will get the same thing. ISA waveform also same thing. The only difference here is in case of alpha is equal to 30 degree, there is no change in the lower half or negative group devices. Okay, there is no change in the conduction sequence of negative group devices. Only thing is upper half devices conduction will be right shifted. Because of that, observe carefully here, this pulse is a small pulse. So what you need to do, alpha is equal to 30 degree. Okay, alpha is equal to 30 degree. 3-phase full converter and 3-phase semi converter waveforms compare. If you compare these two waveforms, you will notice that this particular waveform is having a small pulse. So earlier it was simply 6 pulses, but now it is one pulse is 90 degree, another pulse duration is 30 degree. That is due to lower half devices are diodes. Okay, and in this particular case, source current waveform having some irregular behavior. Okay, so In this case again we plotted waveforms for alpha 0, 30, 60 and 90. Okay. Now here what are the important factors? Now I will give you a small exercise here. V naught IS1 IS DF DPF THD in IS. Okay, you just write down all of these formulas for single phase full converter, single phase semi converter, three phase full converter, three phase semi converter. Make one table. Okay, so that you need not to revise all of these pages again and again. All of those formulas will be at one place. Generally students used to write me some emails, sir, make that table and give it to me. I will not give that. Okay, again don't ask me that table again. So it is for your practice. If you write down, then only you will understand. Until unless if I am supplying a material, you will not able to answer any question. So this is about total harmonic distortion. Till now we discussed up to three phase semi converter. Now at this stage just question yourself, what could be the next topic? Three phase full converter with source inductance. Okay, so concept is same as that of single phase full converter itself. The only thing is, when source inductance is considered, there is a reduction in some voltage. Okay, so how much that voltage is? One more difference from three phase to single phase full converter by taking source inductance into account. If you see, during any overlap interval, there are three devices only in conduction. And how many devices are there in the circuit diagram? There are 6 devices. Out of 6 devices, only 3 devices are in conduction during overlap interval. Because of that, output voltage is not 0 during overlap. Whereas in single phase, during overlap, all the 4 devices in the circuit are in conduction, hence the output voltage was 0. Okay. So if we continue that analysis, there is a reduction in the average output voltage. Let me show you that what is the reduction in the average output voltage, right? So the voltage drop in the source, output voltage due to source inductance is 3 VML by pi cos alpha minus 3 omega ls by pi into I naught. Remember, this number is 2 in single phase, 3 in 3 phase. Okay. So during overlap, as the 3 devices are in conduction, output voltage can be expressed like this. This particular circuit will give you these equations. Okay. So overlap angle can be calculated with this expression, right? Now in this particular lecture I talked about HVDC. Okay, HVDC. So anyhow, I already explained in the video, but HVDC is not part of GATE syllabus. Therefore I can tell you, you can leave this particular topic. Okay, and a dual converter will give you 4 quadrant operation. Whenever it is required to operate the DC motor in 4 quadrant modes. What are the 4 quadrants of operation? Forward motoring, reverse regenerative braking, reverse motoring and forward regenerative braking. Okay, so these what are the topology for single phase or 3 phase full converter? 2 full converter bridges are connected in back to back, also known as anti-parallel connection. We'll give you this three-phase or single-phase dual converter. All right. Let us discuss the revision plan for chapter 3. So this DC to DC converters chapter is quite easy in comparing with the rectifiers topic. Okay. Now here, if you see the basic definition, DC to DC converters, that word itself will tell you that the input power is DC power, output power is also DC power. Okay. So basically these DC to DC converters will transfer, the keywords here, transfer the DC power from one circuit, that is input, to the output circuit. Okay. So by using this DC to DC converters, it is possible to get in the sense, it is possible to control the output power by varying the voltage or by maintaining the fixed voltage. Okay. So we can say as a definition, fixed voltage to variable voltage and vice versa. Okay. So at the output side, fixed voltage generally is used for regulated power supplies. Output side, variable voltage generally used to control the drives, the speed control applications. Okay. So and another keywords here, in high power applications, these circuits are generally referred as choppers. In this particular topic, high power, it doesn't mean that in the order of megawatt, just like in the rectifiers were used in the HVDC systems. The high power itself, comparatively overall power levels, it is somewhat low powers. And low power applications means it is very low power. Okay, so in the order of up to 500 watt or 1000 watt, like that. Such circuits are called SMPS or SMPC. Okay, so in GATE exam only choppers topic is there. SMPS, SMPC, switched mode power supply or switched mode power conversion, this topic is for engineering services exam only. Okay, for GATE exam and PSUs only choppers topic is there. Okay. Now in our regular course, while designing these or realization of DC to DC converters, we discussed certain rules. Okay, at any point of time these rules must be followed. So what is that rule number 1? Okay, so that is, sources should never be overloaded or overstressed. Very important basic rules here. So sources, we have voltage source and current source. Voltage source should never be short circuited. Okay, that is a short circuited. Current source should never be open circuited. Okay, so voltage source should never be short circuited, current source should never be open circuited. This is the rule from sources point of view, right? Now the second rule, this is from elements point of view. What is that? Energy flow in storage elements should never be interrupted. Okay, so in our electrical engineering, what are the circuit elements that can store energy? Okay, those are inductor and capacitor. Inductor can store energy in the form of magnetic field or in the flux will establish, so that further we can define the energy stored in it. Capacitor can store energy in the form of electric field. Okay, so capacitor rule is analogous to voltage source rule. What do you mean by that? Capacitor should never be short circuited. Inductor rule is analogous to current source. So that is, inductor should never be open circuited. Okay. So by the way, what do you mean by current source? A large inductor is placed in series with a voltage source. You should never be open circuited. So by using these rules, we framed three topologies. The first topology is buck converter. Okay. So the nature of power conversion in case of buck converter is voltage to current conversion. The nature of conversion in case of the second topology, boost converter, is I to V. That means the source is current stiff, load is voltage stiff. Now the third topology is V IV conversion. Input and output stages both are voltage stiff nature. In the middle there is a current stiff nature. Okay. So these three topics, buck converter, boost converter and buck boost converter, are in the scope of undergraduate level. Okay. Of course there are few more topologies. I will give you just the names. Shook converter, another is Sepic converter. Okay, another is a Sepic converter. These two circuits are not in our syllabus, right? So we can quickly revise these three circuits. What are that? Buck converter, boost converter and buck boost converter. Now, so the most important thing in this particular chapter is identification of given circuit diagram. Sometimes if you look into the previous GATE problems or previous PSU problems, most of the cases the question will be given in such a way that in the following DC to DC converter, generally the name is not mentioned in the question. That means the examiner is expecting from you to identify the circuit diagram properly and apply the appropriate formula. Okay. So another important point is, in case of these circuit identification, SPDT switch is very important. The position of SPDT switch is a very important here. So that SPDT switch can be replaced with one switch and one diode. Okay. So in place of this switch, what are the devices that we can use in place of this switch? You can use any controlled switch. You can use any controlled switch. Can you tell me what are the various controlled switches? Can we use SCR? Yes. Answer is yes and no. What is the reason for yes answer? Okay. SCR is a controlled switch, we can use it. But what is the reason for no? That is, if SCR is used in the place of switch, as the source is DC voltage source, turn off process of SCR is complicated, because in order to turn off SCR, one of the basic requirement is negative voltage should be applied across anode and cathode terminals whenever current has zero crossing. So as the source is DC, that is not happened here. Therefore present days SCRs are not economic choice in case of these DC to DC converters. So what are the economic choice? Transistor family devices. So nowadays the trend is, the very popular devices for these DC to DC converters are MOSFET. Let me write down here. MOSFET and IGBT. MOSFET and IGBT are the popular devices in place of the switches. Okay. Now, what is the purpose of diode here? For example, when the switch is closed here, the current will flow in this direction. Okay, the current will flow in this direction. Therefore, in that process, inductor will have some stored energy. Suppose if the switch is open circuited, the switch is open, in that case inductive current will freewheels through the diode in that way. So what is the purpose of diode here? That is to provide freewheeling path for inductor current when the switch is open circuited. Okay. So in order to understand the definition of this circuit, just you need to write down basic KVL and KCL equations when the switch is on and off. Accordingly, you can give the circuit names. Anyhow, we will see that in the further pages. So the second topology that is in our syllabus is boost converter. Okay. So in boost converter, the important thing you need to memorize or practice, that is the switch position. Okay, that is a switch position. How did we get these topologies? That we already explained in very clear step-by-step procedure in the videos. Okay, if you don't remember, you just watch those videos once again. Now in this particular circuit, at this stage, what is important for me, whenever the switch is on, what is the direction of inductor current? The blue color arrow is the direction of the inductor current. So inductor will store some energy. When the switch is turned off, the current will, means the inductor current will freewheels through diode in that path. Okay. This is the basic idea of boost converter. We'll see the equations slowly. Now, the third topology is buck boost converter. Okay, the third topology is a buck boost converter. Here also the important thing is the switch position. Switch position is very important. Okay, suppose if the examiner want to test your understanding, they can give switch in a different locations. In the 4 options they can give different varieties, and you need to identify the correct configuration from the realization point of view also. So on what basis we had that conclusion? Voltage sources or capacitors should not be short circuited, inductor or current sources should not be open circuited. Based on that, we gave switch position like that. Okay. Now coming to this buck boost converter, when the switch is on, the current will flow in this direction. I think there is a small error here, arrow should be downward. Okay, in the notes you please make that correction. So when the switch is turned off, inductor current suddenly cannot reverse, therefore it will continue to flow in the same direction, but it will freewheels through diode. That is the reason in case of, now observe very carefully here, in case of buck boost converter, diode position is like this. In case of boost converter, diode position is like that. Okay. On what basis we gave diode connection in that way? That is to allow inductor current to flow smoothly when the switch is turned on and turned off, right? Now, in order to analyze these circuits, there are 2 key principles. What are that? One is volt-second or flux balance concept for inductor. What do you mean by that? Sudden change of energy in any component is not possible. Based on that, for an inductor in steady state, we had a conclusion of volt-second balance equation. According to this concept, in steady state, average voltage across inductor is 0. Okay. Coming to capacitor, amp second balance. Coming to capacitor, amp second balance, which is also called charge balance equation for capacitor. So, in this particular case, the conclusion is average current drawn by capacitor is 0. Okay. So, in order to understand or analyze these DC to DC converter circuits, step by step what you have to remember, voltage source or capacitor should not be short circuited, inductor or current source should not be open circuited. Next rule was, for an inductor we should apply volt second balance, that is in steady state average voltage across inductor is 0. For capacitor we should apply amp second balance concept, that is in steady state average capacitor current is equal to 0. And another important definition, duty cycle ratio. Now remember, in case of rectifier circuits, the control parameter is firing angle, right? But in this particular case, the control parameter is duty cycle ratio. It is the ratio of how much time the switch can be turned on over a cycle time. Okay, that is a duty cycle ratio. So by using this definition, in place of T on, we can write D multiplied with the T. In place of T off, we can write 1 minus D total multiplied with T. Okay. So these are the basic concepts in order to analyze the three basic topologies, right? Now with that, let us look into the equations one by one. Now here, what is the step by step procedure we learned in our regular course? The first step is draw original circuit diagram. Second step is, when the switch is turned on, that is from the interval 0 to dt, just now I told dt is nothing but turn on time. Draw the equivalent circuit first, and then draw the equivalent circuit when the switch is turned off. Okay, switch is turned off. Now if you want, just for your ease of understanding, for an inductor, give some terminal names. This is the procedure I followed throughout the course. What is voltage across AB terminals? Terminal A is connected to VDC, B is connected to V0, and hence we wrote KVL equation is L into di by dt is equal to VDC minus V0. Similarly, in the second interval, L di by dt. Now A to B voltage, I can simply say it is minus V0. So let us call this is equation number 1 dash. In your notes, that might be the notation. So similarly, if you write KCL, sum of the entering currents. So IL is entering current. Now leaving currents, if you want to draw the directions, these are like this. Okay. So capacitor current I can write C into dV0 by dt plus V0 by R, current through a resistor, is equal to inductor current. Let us write this is equation number 2. The same procedure can be applied for boost and buck boost also. Similarly, in this interval KCL equation is the same thing. Okay. Now, by writing volt second balance equation, so what you can do here, during on state term can be multiplied with the dt, off state term can be multiplied with 1 minus d into t. I have equated to 0. What is the reason for that? Reason is, in steady state average voltage across inductor is equal to 0, right? So just by mathematical adjustment we will get V naught, average output voltage equation, is equal to D into VDC. Okay, D into VDC. So as D is less than 1, remember in any numerical problem, if you get D value is greater than 1, D value is greater than 1, there is no more second thought. Your calculation, you might did some mistake. Okay, D value should always less than 1. What is the reason for that? D is nothing but ratio of turn on time divided by total time. So turn on and turn off time together is called total time. Therefore definitely T on is less than T, hence duty ratio will always less than 1. Duty ratio will never be greater than 1. In case any numerical problems, if you get by mistake D greater than 1, it is one checkpoint. Don't substitute whatever value you got blindly. So buck converter, we will get average output voltage always less than source voltage. In the similar line, by applying KCL, by applying for KCL amp second balance equation, we will get IL is equal to V naught by R or D into VDC divided by R. Now from this original circuit diagram also we can have this conclusion. Suppose in steady state, how can you express inductor current? IL is equal to capacitor current plus load current. In steady state, average value of current drawn by capacitor is 0. That is the reason we got capital IL. What is capital IL? Average value of inductor current is equal to average value of load current. That is why we got this conclusion like that. See, in this particular circuit analysis, original circuit, equivalent circuits, corresponding equations. If you are confident enough to write down these equations quickly even in the exam hall also, any problem is given in the question, you are able to answer it. All of the waveforms calculations are derived from these equations only. This is the basic concept. Always try to focus and get command over fundamentals. Fundamental analysis is very, very important. Okay. Now, expression for delta IL, these are just mathematical equations. Now, let us look into waveforms here. See, for the 3 circuits, okay, for the 3 circuits, as a course is already completed, you can have an idea. Of course, in the regular class, I might not explain in that way. So, for the 3 circuits, you will get all the waveforms in a similar manner. You will get all the waveforms in a similar manner. Only difference you will notice, in inductor current waveform, you will notice the differences in slopes only. We will get differences in slopes only. So during on time, what is the slope? How can you find out that? So suppose if you forget that, you have to imagine the circuit diagram first. In buck converter, when the switch is on, inductor will be connected between voltage source and the output voltage. Therefore, you will get rising slope VDC minus V naught upon L. When the switch is turned off, the inductor will be connected to minus V naught. Hence, you have minus V naught by L. Similarly, if you remember the circuit diagram for boost and buck boost converters, you can easily identify. Just pause the video now and question yourself. In boost and buck boost converters, when the switch is on and off, inductor connected between what voltages? So from that you can get slopes. Now in the three circuit diagrams, okay, again I will not repeat these things for boost and buck boost. Follow carefully. For these three circuits, whenever the switch is on, that means from 0 to dt, inductor current will flow through switch. Okay, inductor current will flow through switch. That is why switch current is equal to inductor current from 0 to dt. So once it reaches to peak value, when the switch is turned off, what happens? There is no path for current to flow through switch for inductor current. So inductor current now will flow through diode. So diodes are placed in the three circuits like that. Okay, what is the function of diode in the three circuits? The moment the switch is opened, inductor current will flow through diode. That is the basic reason. So you can remember blindly like this. From 0 to dt, switch current is same as inductor current. dt to t, diode current will be same as inductor current. Okay, and one more important point that you need to remember in the numerical questions. See, for example, sometimes it will be mentioned that inductor current is ripple free. Sometimes it will be mentioned that inductor current will be ripple free. So if delta IL is equal to 0, what do you mean by that? If delta IL is equal to 0, then you will get this waveform, switch current waveform is simply a rectangular pulse. What is the reason for that? Inductor current is given that ripple free. Again, diode current is also having a rectangular pulse like this. This type of rectangular pulse is true only when inductor current has a ripple free. So what type of questions we can expect generally? Some data will be given and assume inductor is large to make sure inductor current is a ripple free in all the three circuits. Find the average value of a switch current or find the RMS value of switch current. Find the average or RMS value of a diode current. The only thing here, you need to identify this particular height. And rectangular waveform, you recollect from the first chapter how to write or how to find average and RMS values for these type of rectangular waveforms. So if you understand the concept and these waveforms, you can do any type of problems given in the question. Now another set of waveforms, voltage across the switch and voltage across the diode. Don't try to memorize or mug up these formulas. These waveforms we plotted by looking into equivalent circuits. If you remember these two circuits, when the switch is on, obviously voltage drop is 0. Therefore, what is voltage across these two terminals? That you have to identify. dt to t interval, diode is turned on, hence voltage across diode is 0. No need to worry about that. What about voltage across these two terminals? That you have to identify. Okay, don't try to mug up these conclusions. Always your starting point for any problem to analyze is this circuit. You have to remember this circuit diagram by practicing number of times. Based on that, any question without memorizing the formulas, you should able to analyze this circuit and you will get the answers for that, right? Next one is voltage across inductor. If you observe carefully here, by substituting the numerical values, you can prove positive area and negative area. So that will give you, or that will be the justification for volt second balance concept. Okay. So most of the people will do mistakes in these two waveforms, capacitor current and output voltage. Okay. So you follow carefully here. Capacitor current is a positive. By look again, this can be interpreted from original circuit. Capacitor current, I can write IC is equal to IL minus I naught. Okay. So that means capacitor current will be positive when inductor current is greater than output current, hence in that interval it will be charging. Whenever capacitor current is negative, when that is possible, inductor current is less than output current. In that interval, capacitor will be in the discharging condition. Okay. So by using those conclusions, we concluded the waveform for capacitor current is a triangular waveform. Okay. So at this instant, capacitor current is equal to load current, and hence inductor current is equal to load current, hence IC was equal to 0. So in this interval, this area will give you how much charge that is stored in the capacitor. So during this charging interval, observe carefully, from this instant to this instant, capacitor voltage, which is nothing but output voltage, will increase exponentially. Okay. Now in these two intervals, capacitor current is negative and hence charge releasing, okay, discharging interval. So in this interval, voltage across capacitor will decrease exponentially. It has some ripple, right? Now these ripples can be calculated, simple mathematical interpretations. Now inductor current ripple can be calculated simply by writing IL equation, and this is a expression for delta IL. Okay. And in case of buck converter, D is equal to 1 by 2 is a, a special case. In that duty ratio, ripple in peak to peak ripple in inductor current as well as capacitor voltage. Inductor current and capacitor voltage both are maximum. Buck converter, D is equal to 1 by 2 is the special case. It will give you maximum value of the ripple condition in both the inductor as well as capacitor voltages. Now another thing is whether the given circuit is operating in continuous conduction mode, boundary condition, or discontinuous conduction mode. That is another important. If you remember the numerical formulas, that is okay. If you don't remember, for that also inductor current waveform is a good point of checking. What is that? See, when you will say this waveform is continuous, this waveform is continuous throughout the cycle, it should not touch x-axis, it should always above x-axis. That is possible when capital IL, what is that? Average value of inductor current is greater than half of this peak to peak ripple. Accordingly, you can conclude, okay, if capital IL is greater than delta IL by 2 here. If capital IL is greater than delta IL by 2. So correspondingly, if you substitute the numericals, you will get the condition like this. 2L upon RT is greater than 1 minus D. In that case, we can say it is a continuous conduction. Suppose if the inductor current waveform just touches x-axis, something like this. In that case, IL will be equal to half of this peak to peak ripple. Okay, IL is equal to half of that peak to peak ripple. That condition is named as boundary condition. So my sincere suggestion, every formula you question yourself, what is the boundary condition for inductor current? If the given circuit is buck converter, what is the formula for that? If the given circuit is a boost converter, what is the formula for that? If given circuit is buck boost, what is the formula? Suppose if you are practicing previous questions, suppose if you are doing a problem related with a boost converter, for example, you question yourself, if the same circuit instead of boost, if it is a buck converter, how to do it? Suppose in the previous GATE exam or previous PSU exam, if you get a problem based on buck converter, you may not get the same problem in the upcoming exams. Okay, so what should be your analysis point of view thinking? Already buck converter problem is given. If it is a boost converter, how should I do it? Suppose already buck boost converter problem is given. If it is a buck or boost converter, how should I do it? Okay, so every formula in the three circuits, what is the corresponding calculation procedure? That should be very clear. Now, if average value of inductor current is less than peak to peak ripple current, then it is called discontinuous conduction. Then it is called discontinuous conduction. So in these three calculations, 2L by RT is called K. On the right hand side, this 1 minus D, it is called critical value for K. Okay. So at boundary condition, you can calculate R critical, L critical by using the previous formulas. Another important thing is discontinuous conduction. Okay, discontinuous conduction. So what do you mean by discontinuous conduction? From 0 to dt, when the switch is on, inductor current will increase. The slope is same as earlier, VDC minus V naught by L. From dt to t, in this interval, inductor current will decreases. But the difference from continuous to discontinuous is this current will reach us to 0 before cycle time. That current will reach us to 0 before cycle time. Okay, that is the instant at beta t. That is the instant at beta t, right? So simply by applying this rising equation and decreasing equation, in case of discontinuous conduction mode, we will get average output voltage is equal to dVdC by beta. Okay, and for the three circuits, we will get output voltage is greater than output voltage in discontinuous conduction mode is greater than output voltage in continuous conduction mode. So I discussed in detail for buck converter. So with this, I can expect you to have quick revising plan for boost. In which direction I will tell you. What are the three steps? First step, draw original circuit for boost converter. Second step, draw the equivalent circuits when the switch is on and off. Write down corresponding KVL and KCL equations. Okay. After then, apply amp second balance for KVL that is inductor voltage equation, volt second balance equation for inductor voltage equation, amp second balance equation for capacitor current equation, and by equating them you will get some conclusions. Now we will see quickly for boost converter. Now in boost converter, this is the original circuit diagram. Okay, this is the first step. Second step, equivalent circuit diagrams in both on state and off state. Third step, KVL and KCL equations. Again, when you are writing KVL and KCL, if you have any difficulty, you can simply write A and B terminals. Okay, and when the switch is on, where A and B terminals are connected, when the switch is off, where A and B terminals are connected. Okay, accordingly you will get KVL and KCL equations. So how to write volt second balance equation? During on state, this voltage VDC should be multiplied with dt. Okay, that is what this term. Off state voltage VDC minus V0 should be multiplied with 1 minus d into t. Then you will get output voltage relation here. Okay, so if you write amp second balance equation for this KCL, capacitor current equation, so on state terms should be multiplied with dt, off state terms should be multiplied with 1 minus d into t. Now by writing I0 is equal to V0 by R, and correspondingly this is another way of expressing average value of inductor current. By using power balance equation, you can get an expression for source current. Okay, now remember carefully here, mostly people used to mug up. Buck converter means multiplying factor is d, boost converter means multiplying factor is 1 upon 1 minus d, buck boost converter means multiplying factor is d upon 1 minus d. Okay, so it should be based on the given question. Always don't try to have that type of vague conclusions. Now in this case again you will notice the waveforms are just similar to buck converter. What are the differences? Only these slopes are different. Okay, now when the switch is turned on, inductor current has a slope of VDC upon L. When the switch is turned off, inductor current has the slope of VDC minus V0 upon L. Okay, rest all the procedure is same. We need not to go into much detail about it. So in this boost converter, the two different concepts, capacitor current and output voltage waveform. Okay, generally most of the students will do mistake here. Let me explain this in detail. So in this particular circuit diagram, again for all questions or doubts, these three circuits are answer to explain. From 0 to dt, capacitor current, this one CdV naught by dt is nothing but IC, okay, is equal to minus V naught by R. Okay, this is a negative here, this is a negative. What do you mean by that? When the switch is turned on in boost converter, follow carefully, same explanation is applicable for buck boost also. When the switch is turned on, capacitor current is negative, that means capacitor will be in discharging condition. Hence voltage across capacitor will decrease. So how to decrease? In order to give that conclusion, we have only one equation, but there are two unknowns. Capacitor current is unknown, capacitor voltage is also unknown. Therefore you should have follow numerical analysis. but instead of complicating the solution, it can be approximated with one assumption. What is that? The ripple in capacitor voltage is very small. The ripple in capacitor voltage is very small. With that approximation, capacitor current is treated approximately constant value, that is minus I naught. And in this particular case, it is governed by first order differential equation. Therefore, these conclusions you can put in the waveform like this. From 0 to dt, capacitor current is negative, that is in the discharging interval. dt to t, capacitor current is positive. Hence, in this area, in this region, capacitor current will be positive and capacitor is in the charging condition. As this capacitor current is negative here, voltage across capacitor will decrease linearly because it is a constant line, it decreases linearly. Okay. Now in this interval, as the capacitor equation was first order differential equation, the rising is in the form of exponential form. The rising is in the form of a exponential form. Okay. So this is how voltage across capacitor, right? Now ripple calculations and all, its a procedure is just like earlier. In this case also, you need to understand how to check the boundary conditions and how to get average output voltage expression in case of discontinuous conduction mode. This equation is another important thing. Now, generally we will get one more situation, that is, suppose if inductor has an internal resistance. If inductor has internal resistance. So even in our regular course also I told this, if any different situations are given in the question, only thing you have to do, first draw original circuit diagram without any non-idealities. Ideal case, draw the circuit diagram. Whatever non-ideality is given, after then you place it. Generally non-ideality, still now this is one area which is not addressed in GATE exam. Non-ideality, resistance of an inductor, internal resistance of an inductor, or sometime the switch can have voltage drop of some voltage, 1 volt or 2 volt, or diode also have some internal resistance or voltage drop. So if you have that type of situations during on interval and off interval, draw the circuit diagrams first, then write down KVL and KCL equations. After then apply volt second balance and amp second balance equations. Accordingly you will get the conclusions. Suppose if I consider some resistance in inductor, we will get average output voltage equation given by VDC multiplied with 1 minus D upon R by R plus 1 minus D whole square. Okay. So one more important point for boost converter. Boost converter should be operated in this region only, up to D max only we should operate. In this region the operation is stable. If D is nearer to unity, then boost converter operation will be unstable. Okay. We should never operate duty cycle ratio is equal to 1 in case of boost. Same conclusion is applicable for buck boost also. Okay. So in these three circuits, you just need to understand very clearly about the first two circuits. If you understand the first two circuits and memorize buck boost converter, these three circuit diagrams, there is no need to repeat the analysis part again. So after this revision video, my sincere suggestion, you take this as homework. So you might surprise, in the revision class also I am giving homework. Okay, it is for your better practice only. For the three circuits, you made one table and write down each and every formula for three circuits. You made one table with a buck converter, boost converter, buck boost converter, three columns. First point, you draw the circuit diagrams. After then, write down what all the various formulas we discussed in all the three circuits. What are that? V0, average output voltage, average output current, average value of inductor current, average value of source current, delta IL peak to peak ripple in inductor current, delta V0 peak to peak ripple in capacitor voltage, conditions for ripple to be maximum. Next, if internal resistance is there, what is the average output voltage equation? The third one is discontinuous conduction mode, what is average output voltage equation? Of course, K critical in all the three cases. In this way, you can revise these three circuits. So, in the DC to DC converter circuits, again I am not going into these waveforms. These three circuits analysis is very important. Okay. Now the next important thing is, anyhow, these are the miscellaneous topics. It's not that much important for GATE exam point of view. Another important thing is circuit diagrams for these types of choppers. Okay, practice these circuit diagrams corresponding quadrants. Practice the circuit diagrams and corresponding quadrants. Type A chopper will give you forward motoring only. Next, type B chopper will give you forward regenerative braking. Remember carefully, rectifier circuits we will not get this second quadrant operation by any rectifier circuit. What is the reason for that? Rectifier circuits, the basic devices are thyristors. Thyristors are unidirectional devices and hence we cannot get negative current. So forward regenerative braking can be obtained only with the type B chopper. Of course, in the dual converter 4 quadrant operation we will get it, but not individually. Okay. Next, type C chopper will give you first and second quadrants. Type C chopper, this topology is almost similar to single phase half bridge inverter. The only difference is this load. In this case, if you have DC motor, it is a type C chopper. In case of inverter, if you have AC load, it will be half bridge inverter. Type D chopper will give you forward motoring, reverse regenerative braking. In case of rectifier circuits, single phase and 3 phase full converter will give this type of operation. Okay. Now type E chopper. Type E chopper will give you all 4 quadrant of operation. In case of rectifier circuits, single phase and 3 phase dual converter will give this 4 quadrant operation. Now after this, what is the next topic? That is commutation circuits. Okay. So what is the basic idea of commutation circuit? If SCR is used in a chopper circuits, the main challenge will be turn off process of SCR. Why? Because in order to turn off SCR, anode current of SCR should be less than holding current, or it should have zero crossing. Okay, voltage across SCR should be negative. These two conditions were not there or not possible to get in case of source with a DC voltage source. Therefore, these two conditions can be created by using L and C components. Okay, by using L and C components. Again, in the commutation circuits point of view, don't care about the given circuit diagram. Generally, the questions will not be on a particular scheme of commutation. Okay, so some LC circuits will be given, write down KVL, apply Laplace transform and try to solve it. Whenever these LC circuits are there, even though source voltage is DC, current flowing through the circuit will have a sinusoidal term. That means it will have some zero crossing in the current. So at that zero crossing of the current flowing through the circuit or SCR will have zero crossing. At that instant, source voltage minus capacitor voltage will provide reverse voltage. This is the basic idea of commutation scheme. Okay, in the regular course we have derived various cases. So what is the first case here? LC circuit with initial conditions 0. Even this approach is useful for your networks analysis also. And second case is RLC circuit. These are the initial conditions. These are the initial conditions. At least try to memorize these equations. Current flowing through the circuit and voltage across the capacitor. What is the third case? This is very general case. Non-zero current through inductor, non-zero voltage across capacitor. Okay, so these two equations need to be derived and practiced. So these are general concepts of commutation. Now what are the specific schemes of commutation? So most importantly, suppose if the question is required to give on the basic of some commutation scheme, current commutation, voltage commutation and complementary commutation. These are the three major schemes that we may get in the objective exam. So the basic concept is very simple here. If TA is not triggered, main thyristor will carry the load current. If TA is triggered, there is a possibility for here resonant current will establish in that path, right? So once that resonant current crosses zero crossing, TA will not conduct further. Therefore, now this capacitor current will flow in this direction. So IT1 plus IC is equal to I0. So by solving that equation, you will come to know that at one particular instant, main thyristor current will be 0. That is the point where commutation will take place. So in this particular arrangement, as the commutation is initiated basically by having zero crossing in the current SCR current first, hence the scheme is named as current commutation. Okay, so if you able to interpret that circuit diagram, these are somewhat useful equations. Okay, so generally in the commutation circuits, what are the important things we need to remember? What is the peak value of main thyristor current? What is the peak value of auxiliary thyristor current? What is the circuit turn-off times for these two devices? Okay. Now, the second mode of commutation scheme is voltage commutation. Now, in this particular case, if TA is triggered, voltage across capacitor will be suddenly applied to T1 and hence the device will be forced to turn off. So here the commutation is initiated by applying a large negative voltage, hence the scheme of commutation is known as voltage commutation scheme. It is somewhat dangerous. Suppose when T1 is turned on, what are the different paths of currents? Load current is one path, capacitor current is another path. Therefore, the peak value of main thyristor is load current plus resonant peak. So in this entire commutations circuits, the key formulas are VDC multiplied with root of C by L. Another is pi by omega. Okay. So where to use and how to use, that you need to analyze. These are the two things. Apart from that, you will not get any difficult formulas in this particular commutation analysis. So these are some of the waveforms. These are some of the waveforms that you will come across. In this particular case, another important thing is output voltage waveform. Okay, output voltage waveform. So in this case, suppose in case of type A chopper, output voltage waveform will be like this. But apart from that, it has some additional portion. You need to calculate area of this portion, add it to original average output voltage, so that you will get two more new terms. What is that? Expression for average output voltage and effective turn on time. Effective turn on time. These are the things that you need to memorize in case of voltage commutation scheme. Another is complementary commutation scheme. Of course, analysis looks quite lengthy. However, you just need to memorize only two formulas. What is the circuit turn off time for each devices? We have formulas here. Circuit turn off time for first thyristor 0.693 multiplied with R1 into C. Circuit turn off time for second thyristor 0.693 multiplied with R2 into C. Okay, so these are the two expressions that we need to remember for this complementary commutation scheme. So in this case, if you observe carefully, suppose if T1 is turned on, voltage across capacitor will suddenly applied to second thyristor. In the similar manner, if T2 is turned on, same voltage across capacitor will suddenly applied across T1 device. This is also one category of voltage commutation. That is what I told. In principle, in a simple terms, there are two major schemes. One is current commutation scheme, another is voltage commutation scheme, and another popular method is natural commutation. Natural commutation we studied in the rectifier circuits. Of course, there is no special focus on natural commutation. Special focus is for these commutation schemes. These are also called forced commutation techniques. Okay, because source is DC, we don't have zero crossing and reverse voltages naturally. In order to create that, external circuit components are required. That is why the special discussion on commutation circuits. So the waveforms are here. From the waveforms, two more things we need to remember. Those are, what is the peak value of T1 current? What is the peak value of T1 current? And circuit turn off time I already told. And what is the peak value of T2 current? Okay, this is another point of interest, right? So these are the different commutation schemes. So in the complementary commutation scheme, what are the things you need to remember? Peak value of T1 current, peak value of T2 current, and circuit turn off time for T1 device and T2 device. Okay, suppose in the original circuit diagram, if R1 and R2 are given equal values, then these values TC1 and TC2 values are also same. So this is about the revision plan for DC to DC let us look into the revision plan for chapter 4, that is DC to AC converters, also called inverters. Okay. In the previous video, we have discussed about DC to DC converters revision plan. Now, comparatively, the previous 3 chapters, this 4th chapter is quite simple. It is not so heavy formulas, very small topic, and concepts should be clear, right? Now, first let us look into the definition. DC to AC converters, also known as inverters. As the name indicates, for these circuits, input is DC power, output is AC power. Now, what is important in this definition is yet required output voltage and frequency. What do you mean by that? By using inverter circuit, it is possible to control output voltage as well as frequency. So, control means, mostly people will confuse here, variable voltage, not necessarily. Controlling means you can vary the voltage as well as maintain the voltage to be constant also. For that also, it requires some control action. So, it has different applications. Now, for example, if you see UPS, when the inverter is used in the application of UPS, normally in household applications, in our houses we will use it. So, what is the category here? Constant voltage and constant frequency type. Speed control of AC motors. In this particular application, the role of inverter is to control or vary the voltage, variable voltage and variable frequency type. So, this particular application is also named as VVF, variable voltage, variable frequency drives. Basically, these type of controls, AC motors are used to control the induction motors. Okay. Next, another important application of inverter circuits, that is reactive power compensation, enhance the stability margin, active filters, right? So, these 3 applications together named as FACTS applications. One of the very important application of inverter circuits in power systems domain, that is flexible AC transmission systems. Okay. Now, coming to renewable energy systems, solar and wind. In case of solar systems, the basic source is a photovoltaic cell. It will take energy from the sun and convert that energy into a small DC voltage. Okay, multiple cells will be connected in series and parallel in order to increase the voltage as well as current levels. That will be given to some DC to DC converter. Again, it will be converted back to AC by using inverters. In that way, inverter will play an important role in solar systems, right? Next, now this is about applications of inverters. The next one is classification of inverters. Basically, inverters are 2 types based on the nature of the source. These are the 2 types: voltage source inverter and current source inverter. So, in case of voltage source inverter, the nature of the source is voltage stiff. In case of CSI, the nature of the source is a current stiff. Okay. So, in case of VSI, what is the switch compatibility? That is unipolar and bidirectional switch. For example, if voltage source input is represented with a capacitor, okay, voltage source input is represented with a capacitor. Capacitor voltage cannot change instantaneously, and hence whatever the switch you are using in VSI, it should be unipolar property. Capacitor can allow the current to flow in both the directions. Therefore, the switch property should be bidirectional switch. So if you recollect from our first chapter switches topic, unipolar and bidirectional feature will be exhibited by MOSFET and IGBT with anti-parallel diodes. Okay. Coming to current source inverter. What do you mean by current source? A voltage source in series with large inductor. Okay. A voltage source in series with a large inductor. So inductor can allow the voltage polarity to change instantaneously, and hence the switches should have bipolar feature, and inductor will not allow the current to flow in both the directions. Therefore the switches should be of unidirectional switches. Okay, so from the first chapter we already studied that SCR and GTOs are having bipolar and unidirectional switch property. Okay. Now coming to voltage source inverter, this particular block depending on the topology of the switches. Topology means the way how various devices or switches are connected. Based on that, the output can be either single phase or three phase. Similarly, for CSI also the output will be either single phase or three phase. Okay. Now one important statement, observe carefully these two statements. Basically these two are dual statements. In VSI, V0 is decided by source, output voltage is decided by source, whereas in CSI output current is decided by source. Output current is decided by source. As you already have these notes, try to go through your notes parallelly when I am explaining, so no need to write again. In case of VSI, output current. In case of CSI, output voltage depends on load parameters. Okay, if you understand these two statements clearly, going to the waveform analysis, for each circuit which waveforms you need to draw, that will be clear. For example, if you are analyzing voltage source inverter, your first focus should be on output voltage waveform. Okay, the next focus, when you are drawing output current waveform, you should consider load parameters, whether it is for resistive load, inductive load or something else. Okay, so voltage source inverter, first focus should be output voltage waveform, which is basically decided by the source voltage. Whereas in current source inverter, the first focus should be output current waveform. It is decided by input current value. Okay, when you are drawing output current in VSI, output voltage in CSI, you should consider about load parameters. Again, one more important point, in voltage source inverter, as the source is voltage stiff nature, you should not place voltage sink at the load side. What is that? Capacitor. Therefore, in VSI load side, you should avoid capacitor. Very, very important conclusion. Especially these conclusions are very useful for PSU exams. In case of CSI, as the source is current stiff nature, you should avoid current sink. Pure inductive load should be avoided. Okay, these are the thumb rules in VSI and CSI. Now voltage source inverter applications are limited to low and medium power applications. Majority of the loads comes under this category. Very high power applications, 100 megawatt motors are very rare. Okay, therefore most of the cases industrial applications comes under low and medium power category. In those cases voltage source inverters will be very useful applications. Coming to CSIs, CSIs are preferable for high power applications. Reasons I will explain a little shortly. Now let us look into the circuit topologies. Okay, now in this particular chapter, if it is clear about half bridge VSA application, full bridge VSA application is just a repetition. Okay, remember in the previous chapter you should be very confident in the analysis of buck converter, so that boost and buck boost are easy. In the inverters chapter, the key concept is half bridge VSI, so that full bridge VSI will be very simple, right? Now first let us look into the switch types, right? So you can just visualize this is an IGBT section, that is one IGBT section. What type of switch it is? That is unipolar and bidirectional switch. Unipolar and bidirectional switch. Now here this particular two switches are together called one inverter pole or inverter leg or inverter limb. The popular terminology is inverter pole. Okay, so the midpoint here A with respect to this 4, in these, between these two terminals the load is connected. Okay, now one of the important operation condition is these two switches should be operated in complementary fashion. What do you mean by that? Suppose when S1 is on, S2 should be off. When S2 is on, S1 should be off. Suppose if both are turned on simultaneously, then what will happen? If S1 and S2 both are turned on simultaneously, then source will get short circuit, isn't it? In order to avoid that condition, S1 and S2 should be operated in complementary fashion. Now the total voltage here is VDC. Who will provide this voltage VDC? External circuit. Okay, it can be some rectifier also. Just from the safety point of view, the midpoint will be grounded. Remember, this might not be the single source. So generally in the inverter circuits, there will be a group of capacitors, capacitor banks. Those capacitor banks will be continuously charged from some external either DC to DC converters or through some solar panels. Therefore, it is nothing wrong to represent source voltage with the two equal halves. Midpoint will be grounded. There will be grounding mechanism. Okay. Now, before looking into these equations, first let us look into the waveforms. So first, these two waveforms are about a switch sequence. What is the switch sequence? When S1 is on, S2 is not given command. When S2 is given command, there is no command for S1 to turn on. Okay. Now for example, if S1 is on, load terminal A will be connected to source terminal X. Therefore, output voltage will be positive. VAO is equal, output voltage is nothing but VAO. So as there is only one pole here, that is also same as a pole voltage. So when S1 is on, VAO is same as VDC by 2. When S2 lower switch is on, this load terminal A will be connected to Y here. In that case, pole voltage or output voltage is equal to minus VDC by 2. Therefore, now see this waveform. As long as S1 is on, we have output voltage is VDC by 2, positive value of the source voltage. When S2 is on, this voltage is same as lower half voltage. But as A is connected to negative terminal, A is connected to negative terminal here, we have considered it is a minus VDC. Okay. So in this waveform, what is important for us? Peak value of this fundamental component is important. Okay. So we had derived that particular equation in the first chapter. Okay, we have derived that equation in the first chapter, 4x by pi. Here what is that x value? VDC by 2. Therefore 4 by pi multiplied with VDC by 2. Remember, peak value of fundamental component of square waveform is equal to 4 by pi into VDC by 2, right? At this stage we don't have any PWM technique. Coming to PWM technique, this formula will have a slight change. So in this particular chapter, whether to use 4 by pi or something else, that is an important thing. So in place of 4 by pi, you will get a modulation index once we started the modulation technique. Okay. So in the square wave mode, peak value of the fundamental component is 4 by pi into VDC by 2. When it comes to modulation technique, that will be modified to MA into VDC by 2. These are the two important formulas that need to be memorized in inverters chapter. Now, coming to resistive load, observe carefully here. When I am discussing about output voltage, I don't bother about what is the load parameters, because in voltage source inverter, what is the basic definition? Output voltage is decided by source voltage. When you are drawing output current, then only you need to look into load parameters. Now, suppose if you take a resistive load, we know that in case of resistive load, output current simply follows output voltage. What is the difference here? Only the magnitude. As output voltage magnitude is VDC by 2, current magnitude will be that value divided by R. That's all. Similarly, negative magnitude is minus VDC divided by 2R. Minus VDC divided by 2R. Here also the same concept. One important point, that is V0, I0 fundamental components are in phase because of the resistive load. Now, for these two waveforms, let us look into Fourier series conclusions. Okay. So these are all known points for us. So in the first chapter, we derived Fourier series equation for a square waveform. What is that? 4 by pi multiplied with VDC by 2 into 1 by n. So this number will give you 2 VDC by n pi into sine of n omega t. Another important point is this waveform contains all odd harmonics and the lower order harmonic is third harmonic. Next one is, what is RMS value of fundamental, what is RMS value of the waveform, and what is a THD. These are very repeated calculations from the rectifiers chapter onwards, hence it is not so hard to memorize these formulas. Okay. So coming to output current in case of resistive load, what are the things you need to remember? As output current is also square waveform, THD is simply 48.43%. Remember, THD of square wave, THD of square waveform is 48.43%. Okay, all cases, irrespective of the magnitude. And another important thing is, in case of resistive load, diodes will not be in conduction. Diode conduction will come into picture for non-resistive load. Now, let us look into inductive load. So inductive load, this particular waveform is drawn by considering non-zero initial conditions. Okay, non-zero initial conditions. Basically, I naught waveform is, what is this waveform? Exponential nature. Exponential nature. Okay, how much time diodes and switches will be conducting? For example, if I take this is T1, this is a T2, and this is a T3. So from 0 to T1 load current is negative. 0 to T1 load current is negative. But in that interval output voltage is positive. Output voltage is positive. Therefore, if you look into the circuit diagram, output current negative, but output voltage is positive. That is possible with D1. Okay, that is possible with D1, and hence diode is in conduction. So what is the guideline to conclude these conduction of switches and diodes? You just need to look into what is output voltage polarity and a current direction, whether it is a positive or negative. Accordingly, which device will be in conduction? Okay, that we need to see. For example, if the load is pure inductive, in that case the conduction interval of each diode and switches are equal. Okay, one very popular question. For example, if the inverter output frequency is 50 hertz, so what is the conduction time of each switch and diode? So total cycle time will be 20 millisecond. In that case, each switch and diode will conduct for a period of 1/4 of that cycle. Okay, that will be 5 millisecond. Now one more point here. In case of pure inductive load, this current waveform is triangular waveform. Okay, this current waveform is a triangular waveform. Now, if you look into leading power factor load, so the output current waveform will start at some angle early. This phi is nothing but load power factor angle. Okay, load power factor angle. So this particular interval should be converted into equivalent time. That time should be equated with circuit turn off time of the device. Okay, what is the application of this particular case? That is overexcited synchronous motor. Okay, overexcited synchronous motor. So these are some of the equations. So this particular equation is important in calculating output current expression for non-resistive loads. Okay, so once you have this Fourier series expression, if you take this equation, it will give you how to find overall RMS value of the output current. By using that, you can find THD. Okay, now coming to pure inductive load, I already talked. This one, leading power factor load, just these are the two things that are important. Load power factor angle should be equated with circuit turn off time. Okay, and one more important thing from the waveforms, in case of inductive load, here the scheme of commutation is forced commutation. This is another important thing. And leading power factor load, the scheme of commutation is load commutation. Okay, load commutation. So in this particular case, for successful commutation, current waveform should have this sinusoidal term. Okay, so that sinusoidal term is possible only when the load parameters are in underdamped condition. What is that? 1 by LC is greater than R square by 4L square. So that is about half bridge VSI. There is only one pole of operation. Now if half bridge VSI is clear, full bridge VSI is a nothing. So you can just visualize this circuit as two half bridge VSIs. Okay, this is one half bridge VSI and this is another half bridge VSI. So two half bridge VSIs are operating in such a way that the phase difference between the two poles is 180 degree in order to produce a square waveform as the output voltage waveform. Okay, so the two poles are operated with a 180 degree phase shift means, for example, if the first pole starts at 0, second pole will start from 180 degree. Only in that way these output voltages will have a slight difference. Now observe carefully here, first pole started from 0. Okay, so this is just nothing but one half bridge VSI output, half bridge VSI output, half bridge VSI output. Okay, this is a half bridge VSI output. The second VBO, this is also one half bridge VSI output. Now follow carefully, these two waveforms have a phase shift of 180 degree. Due to that, the resultant output voltage, what is the resultant? V0 is equal to VAB. VAB is nothing but VAO minus VBO. So from 0 to pi, VAO VDC by 2 minus of minus VDC by 2 will give you VDC. In that way, output voltage will be square waveform. Okay, so only difference in the Fourier series equations, that is earlier in that equation at this place it was 2, but now it is 4. Rest all the explanation is same. Okay, R load output current waveform is same as earlier, the square waveform only, and here it is a I0 waveform for inductive load, pure inductive load, leading power factor. All the waveforms are same. Only the difference is earlier here single device was in conduction, but now it is pair of devices are in conduction. Okay, and equations wise all are same thing. Only difference here, earlier it was 2, but now it is a 4. Okay, that is just because of the magnitude is 2 times of the previous one. These equations also same as earlier. So that is about single phase inverter circuit. Now the next topic is 3 phase full bridge VSI. Now in this particular case, observe carefully, there are 3 poles. There are 3 poles or 3 half bridge VSIs are connected to same source. 3 half bridge VSIs are connected to same source. So these 3 half bridge VSIs will be operated with a phase difference of 120 degree in order to produce a balanced 3 phase voltages at the load side. Now here each switch should be of unipolar and bidirectional feature. Okay, each switch from S1 to S6 will have unipolar and bidirectional feature. Now in this case there are 3 different types of voltages can be defined: pole voltages, line voltages and phase voltages, and VAB is the difference of 2 pole voltages. Okay, similarly you can define it. Now this particular circuit working principle can be explained with the 2 conduction modes, 180 degree and 120 degree conduction mode. Okay, so 180 degree conduction mode means, as the name indicates, switches are operated, okay, with a conduction period of 180 degree and the phase difference between any 2 poles is 120 degree. So for this particular circuit to understand what is required for us, first you need to draw pole voltages clearly. If you are able to draw pole voltages, rest all the waveforms you can find out easily. So VAO, what is VAO? This is 1/2 bit VSI waveform. From 0 to pi, half of the cycle S1 is on. Okay, therefore output voltage is VDC by 2. For the remaining half of the cycle, S4 is on, lower half of the same pole. Similarly, the same square waveform you have to draw with a 120-degree lag, another 120-degree lag, so that you will get VAO, VBO and VCO. Okay, so I can say here these three waveforms are pole voltages. These three waveforms are pole voltages. Next, in order to draw line voltages, what you have to do? VAB, what is VAB? VAB is equal to VAO minus VBO. At every interval you have to take the difference of that, then you will get this quasi square waveform. Okay, so these three waveforms are line voltages. Okay, these three waveforms are line voltages. So in order to draw phase voltages, you need to have step calculations. Each step calculations you have to draw the equivalent circuits, and if you go through our earlier video you will understand, but I am not going to that. If I start that explanation, it is again a repetition. So you will get a 6-stepped square waveforms. So what is important to remember in this discussion, 180-degree conduction mode, pole voltages are square waveforms, magnitude wise VDC by 2. Line voltages are quasi square waveforms, magnitude is VDC. Phase voltages are 6-stepped square waveforms. Each step magnitude is VDC by 3. Each step magnitude is VDC by 3. If you remember these things, the next step could be write down Fourier series equations. Okay, next step is write down Fourier series equations. Okay, so these are Fourier series equations for pole voltages. These are simply a square waveforms. Next, quasi square waveforms Fourier series equations also we discussed in the first chapter Fourier series topic. So from that, see what are the things that will be used in the problems. Okay, RMS value of fundamental line voltage, RMS value of line voltage, RMS value of phase voltage. One more thing here, that is RMS value of fundamental phase voltage. Okay, so 120-degree conduction mode. First of all, what is the basic necessity to study about 120-degree conduction mode? If you see in this 180-degree, at this instant S1 is turned off, at the same time S4 is turned on. There is a quite chances for S1 and S2 conducts for even for a short interval also, there is a quite chances for source to get short circuit. In order to avoid that, the next common practice is 120-degree conduction mode. Now observe carefully here, S1 is turned off 60-degree early, so that it conducts for a period of 120 only. Like that, each switch will conduct for a period of 120-degree, and correspondingly you will get pole voltages in this particular operation quasi square waveforms. Okay, so once you draw pole voltages, the next procedure is a line voltages. and then by using equivalent circuits you will come to know here pole voltages and phase voltages are same. So at least I hope you have this table. If not, at least prepare this table after this video. Okay, so from this total discussion, what is important for us? You make a small table, that is in 180-degree conduction, in 120-degree conduction. Okay, VL, V phase, VL1, V phase 1. Prepare this table. Very important. That table is enough in order to solve three-phase or voltage source inverter problems, right? The next topic what we discussed in our regular class, that was single phase current source inverter. Okay, it's a very simple topic. So in this particular circuit, our first focus is output current, because it depends on source. It depends on source. Okay, so once we got output current waveform depends on the load parameters, we need to draw output voltage. Okay, output voltage. So in case of resistive load, output voltage will have simply output current waveform shape. Waveform shape wise both are similar. For capacitive load, output voltage here is triangular. In case of voltage source inverter, output current was triangular, but now output voltage is triangular. Okay, and here some of the these equations are very simple, no need to have any difficulty to remember this. What is the circuit turn off time? In case of VSI, what is the conduction time of each switch? What is the peak inverse voltage? Right, now this is another circuit. Till now this question has not addressed in our exam, but anyhow, in case of DC circuit, a circuit with a DC source, okay, so the difficulty is commutation of thyristors. In order to get successful commutation of thyristor, this capacitor will be placed. Okay, so by using that capacitor, the waveforms will be modified. A little differently. See, earlier triangular waveform, now it is modified to exponential waveform. In this particular topic, what is important thing? If at all any question comes, you can expect a question on this particular equation, circuit turn off time. Anyhow, I already explained one numerical example, various calculations in the regular class. You can just go through it, right? Next one is three-phase current source inverter. In this particular case, the key points are at this particular instant. Okay, current has di by dt is equal to infinity. Because of that, there is a quite possible that output side to have large voltage surge. Okay, that is the only thing we need to remember in three-phase current source inverter. In order to suppress that large voltage surge, a three-phase capacitor bank will be placed across the three-phase load. Okay, suppose if at all any question, if the examiner want to prepare or frame, what is RMS value of this output phase current, quasi square waveform, you can find out RMS current, or what is a peak value of fundamental current. Okay, so you can draw the fundamental component like this, then you can frame, or what is the equation for that from the quasi square function. Okay, it's not so difficult. So in case of this particular 3-phase CSI, it is preferable for the loads to have less leakage inductance. Okay, for the loads to have less leakage inductance. Generally, that property will be exhibited by high power induction motors. Okay, so this is about a 3-phase CSI. Next one is try to do these skill assessment problems. These are interesting questions. Please practice those questions. The next one is voltage control in inverter circuits. Okay, so these two methods generally not used. So from the examination quick revision point of view, no need to spend much time in that. You can directly go to internal control. Okay, so internal control, you just need to understand in a high level side. This is very important topic. GATE exam also, the main potential in from this topic only, inverters topic. What is a PWM technique? What is the objective of that? Okay, so suppose if you don't apply PWM technique, inverter circuit output voltage is a square waveform. It has all odd harmonics. It has all odd harmonics. So lower order harmonics are always troublesome factors. So in order to reduce the filter size, it is preferable to eliminate lower order harmonic components within the circuit itself. Therefore, in that particular aspect, a PWM technique is popular. Okay, so what is a PWM technique here? The two poles of inverter circuit will be operated with a phase difference other than 180 degree, so that output voltage will have pulsed manner, right? So suppose if the two poles of inverter circuit are operated in such a way that output voltage has a pulse width of 2D, that pulse width is symmetric with respect to pi by 2 in the positive half cycle. Okay, in a similar way, the same pulse width of 2D is a symmetric with respect to 3 pi by 2 in the negative half cycle. Okay, so because of this way of producing the output voltage, we can see some benefits. You will understand that benefit from Fourier series equation. For example, if you derive the Fourier series equation for this particular quasi square function, you recollect from first chapter, we will get Fourier series expression for that particular single pulse width modulation output voltage equation is like this. So one of the important aspect here is this term sin ND. Okay, for example, if you select ND is equal to pi, or 2D, where 2D is a pulse width, 2D is equal to 2 pi by n, then what it will tell you that output voltage will be free from nth harmonic. Okay, I think I gave this point in the next case, right? See, if ND is made equal to pi, or 2D is equal to 2 pi by n, in that case single pulse width modulation output voltage will be free from nth harmonic. For example, if third harmonic is the target, then what is the concept here? Pulse width should be maintained to 2 pi by 3. Then output voltage will be free from third harmonic. Okay, so in that case, what will be RMS value of the output voltage? What is the RMS value of output voltage? VDC multiplied with under root 2D upon pi. Okay, so in single pulse width modulation, the key points that need to be practiced: Fourier series derivation or Fourier series conclusion. What should be the pulse width in order to eliminate a particular harmonic? If it is a third harmonic, pulse width should be 2 pi by 3. If it is a fifth harmonic, pulse width should be 2 pi by 5 or 72 degree. Okay, Now RMS value of the output voltage is VDC multiplied with root of 2D by pi. Up to this single pulse width modulation, the main strength is it can eliminate one specific harmonic component in the output voltage. However, lower order harmonic content will be still significantly somewhat high. In order to reduce lower order harmonic content further lower levels, the next practice is the 2D pulse width. Earlier in the positive half cycle, the pulse width of 2D. Now the 2D was divided into two parts, each pulse having a width of D and D. This is a symmetric with respect to pi by 2, just like earlier. Okay. Similarly, the same 2D with the D and D is symmetric with respect to 3 pi by 2 in the negative half cycle. So, if you compare these two waveforms, in single pulse width modulation, 2D pulse is symmetric with respect to pi by 2 in the positive half cycle. In the multiple pulse width modulation, the same 2D was symmetric with respect to pi by 2. But what is the difference here? Earlier it was a single pulse, now it is divided into multiple pulses. The reason in dividing into multiple pulses is if you do or if you control the inverter output in this manner, Fourier series will tell you that lower order harmonic content can be reduced to the great extent. Okay. So how many more pulses we can go? That depends on the switching speed capacity of the power semiconductor devices. So in this aspect, in PWM circuits, fast switches are more preferable. Okay, fast switches are more preferable. But when you are dividing a given pulse of 2D into multiple pulses, what is the objective? See, earlier RMS value of the output voltage is VDC into root of 2D by pi. So, in the multiple pulse width modulation, you can divide the given pulse 2D into as many as pulses, depends on the switch capacity, switching capacity, okay, switching speed, but in such a way that RMS voltage should remain same as earlier equation. Earlier it was VDC into root of 2 by pi. Now each pulse is divided into 2D by n, so that n and n cancel, it has the same equation as of earlier. So while dividing the pulse in this way, RMS value of the output voltage remains the same, but it can be proved that lower order harmonic content can be reduces to great extent. Okay. So that is what multiple pulse width modulation. Now this particular diagram will explain what is the basic idea of generating these pulses. In the PWM circuit, basically there is one comparator circuit. For this comparator circuit, there are two inputs. Okay, one is a carrier signal, another is a reference signal. Depends on the comparison logic. These two inputs, see, triangular waveform is a carrier signal, and horizontal red, this one, square waveform is given as a reference signal. Based on the comparison logic, these pulses will be produced. Okay, now these pulses will be given to switches in the inverter pole. So whenever these pulses are positively high, upper switch will be controlled. Whenever these pulses are negatively high, lower switch will be controlled. Accordingly, output voltage will be having a pulsed square waveform rather than continuous square waveform. It will have a square waveform with the multiple pulses. What is the advantage of having multiple pulses? Lower order harmonic contents can be reduced to great extent, so that the filter size, okay, bulky filters can be avoided. That is the main theme of a PWM technique. Okay. Now In this PWM technique, there are two parameters that are very important. Modulation index. One is amplitude modulation index, another is frequency modulation index. This MA will play an important role in the selection of number of amplitude of the fundamental component of output voltage. This MF will play an important role in the selection of number of pulses per half cycle. Okay, so now earlier I have shown that a comparison between triangular waveform and a square waveform. Suppose if the reference waveform is replaced with a sinusoidal, then it will be called a sinusoidal pulse width modulation technique. In this particular sinusoidal pulse width modulation, the important formulas are this one. This is a very important, and one question is for sure. If it is single phase half bridge VSI, now follow these expressions carefully. If amplitude modulation is modulation index, if amplitude modulation index is less than 1, peak value of fundamental output voltage VO1 cap is defined as VDC by 2 multiplied with MA. Okay, MA. Suppose if it is a square wave mode of operation, that VDC by 2 should be multiplied with a 4 by pi. This is the only difference. Suppose if it is a full bridge VSI, VDC should be multiplied with MA in PWM technique. VDC should be multiplied with a 4 by pi in case of square wave mode. Okay. Anyhow, we have already derived all of these equations in the regular class. So these are important things. Now, in case of 3-phase full bridge VSI, observe carefully. You compare with the single phase and a 3-phase. Instead of MA, now the term is root 3 by 2 root 2 into MA, right? Now, if it is a 180-degree conduction mode, it is a simply quasi-square waveform, and the multiplying factor will be root 6 by pi, right? So, in these 3 cases, there are previous 4 gate questions. So, follow these equations carefully. So, this is about revision plan for inverter circuits. So, in the inverter circuits, what are the important things? Single phase half bridge VSI and Fourier analysis, and single phase full bridge VSI, waveforms and Fourier analysis, 3-phase inverters, 180-degree and 120-degree conduction mode, current source inverter, and PWM technique, sinusoidal modulation, single pulse width modulation, multiple pulse width modulation, and formulas with this MA are important. With this, I am concluding. Thank you.